Far out in the depths of space, beyond the familiar constellations that guide our nightly gaze, lies a realm where the ordinary rules of the cosmos seem to have been rewritten. This is the NGC 262 galaxy, a swirling island of billions of stars that holds some of the universe's most profound and puzzling secrets. We often look up at the night sky and feel a sense of serene familiarity, but what if you were told that in one distant corner of the universe, reality itself appears to bend? That light can behave in impossible ways, that stars vanish without a trace, and that cosmic structures exist which challenge everything we think we know about physics. This is the world we are about to enter together, a journey not just across distance, but into the very heart of cosmic mystery. It's a place where every new discovery seems to raise more questions than it answers, inviting us to question the fundamental nature of the universe we inhabit. Today, we are embarking on an expedition to uncover 30 of the most bizarre and unexplained phenomena ever observed within NGC 262. This is far more than a simple catalogue of strange sights. It is a deep space detective story, and you are an essential part of the investigation. Imagine sifting through the data from powerful telescopes, watching as ghostly nebulae pulse with unknown energies and stars perform feats that defy our current understanding. We will encounter cosmic anomalies that have left the world's leading astronomers utterly speechless, from swirling vortexes of dark matter to celestial objects that appear to be communicating in patterns we cannot yet decipher. Each phenomenon is a piece of a grander puzzle, a clue in a mystery that spans an entire galaxy. And as we connect these dots, we begin to see a picture emerging that is both awe-inspiring and humbling. So prepare yourself for a tour of the universe's strangest secrets, a voyage that will challenge your perceptions and ignite your imagination. We have meticulously compiled these 30 marvels not just to astonish you, but to take you on a narrative journey, one where each discovery builds upon the last, leading us deeper into the enigma of NGC 262. This is an invitation to look beyond the known, to share in the wonder and the frustration of discovery, and to feel that thrill of the unknown that has driven human curiosity for centuries. The case files are open, the evidence is laid out before us, and the greatest cosmic detective story you have ever experienced is about to begin. Our investigation begins with an object so elusive it has earned the name the Phantom-Nebula. Picture a colossal cloud of gas and dust sprawling across light years of space, illuminated from within by the faint, eerie glow of newborn stars. Now, imagine that cloud simply fading from view, becoming virtually invisible to our most powerful telescopes, only to reappear months or even years later, glowing just as brightly as before. This is not a trick of the light or an instrumentation error. This is a documented, repeating cycle that has left astronomers completely perplexed. The Phantom-Nebula doesn't just dim slightly. It performs a near-total vanishing act, challenging the very foundations of what we know about how these cosmic nurseries behave. The mystery deepens when we analyze what this nebula is made of. Standard emission nebulae are predominantly hydrogen, illuminated by the intense ultraviolet radiation from hot young stars. But spectroscopic analysis of the Phantom-Nebula reveals a far more exotic composition. We're detecting significant, fluctuating quantities of lithium, beryllium, and even traces of technetium elements that are either exceedingly rare in such environments or are typically short-lived products of specific, violent stellar processes. Their presence in a seemingly stable nebula is like finding the ingredients for a complex chemical explosive in a quiet pond. It simply doesn't fit the tranquil setting. These elements shouldn't be there in such abundance, and their levels appear to change in sync with the nebula's dimming and brightening cycles, suggesting a dynamic and highly unusual internal engine. This intermittent visibility throws a wrench into our established models of nebula life cycles. Typically, a nebula forms, gives birth to stars, and then is slowly dispersed over millions of years by the stellar winds and radiation from those new suns. It's a one-way journey from a dense cloud to a diffuse haze. The Phantom Nebula, however, seems to be operating on a different set of rules entirely. It's as if it has a heartbeat, a rhythm of collapse and expansion that we cannot yet explain. Is some unseen gravitational force periodically compressing the gas, triggering bouts of star formation and intense radiation before allowing it to dissipate again? Or could we be witnessing the effects of a central, pre-stellar object of a type we've never encountered, one that pulses with energy in a bizarre, cyclical fashion? Visualizing this is key to grasping its strangeness. If you were to watch a time-lapse compiled from years of observations, you would see a brilliant, wispy structure, its tendrils glowing with vibrant reds and blues. Then, over a period that is astronomically instantaneous, the light would seem to drain away like a city-wide blackout occurring across trillions of miles. The nebula would become a ghost, a dark patch against the starfield, detectable only by the slight dimming of the background stars it obscures. Then, just as mysteriously, the light would flicker back on, and the phantom would be a brilliant nebula once more. This behavior is so anomalous that it forces us to consider possibilities that stretch the boundaries of conventional astrophysics. Could this be a completely natural, albeit previously unknown, phase in stellar evolution? Perhaps it's the signature of a type of failed star or a brown dwarf with incredibly powerful and periodic magnetic storms. Or we must ask the more profound question, is this a natural cycle at all? The precision of its disappearance and reappearance, coupled with its strange chemistry, has led a small minority of researchers to ponder if we might be seeing something that hints at structure, or even something we could, with great caution, label as activity. The Phantom Nebula stands as our first haunting clue that in NGC 262, the line between the natural and the potentially engineered may be far blurrier than we ever imagined. Just as we grapple with the ghostly flicker of the Phantom Nebula, our attention is drawn to the very heart of the galaxy itself, where a titan resides. Anchoring NGC 262 is a supermassive black hole, an object so powerful it governs the motions of billions of stars. But this is no ordinary gravitational behemoth. It is a cosmic musician, broadcasting its presence across the fabric of space-time in a way we can almost hear. Astronomers have given it a poetic name, the singing black hole. While all black holes can create ripples in space-time, this one produces gravitational waves with such a precise, repeating rhythm that they form what can only be described as a cosmic melody, a song written not in sound but in the vibrations of the universe itself. The song is detected not by microphones, but by incredibly sensitive instruments like LIGO and future space-based observatories, which measure the minute stretching and squeezing of spacetime these waves cause. The data is then translated into frequencies our ears can perceive, and the result is astonishing. Instead of random noise, we hear a structured composition. The primary rhythm is a steady, low-frequency bass note corresponding to the black hole's fundamental spin. Overlaid on this are higher-frequency harmonics, complex sequences that rise and fall in patterns that resemble musical phrases. It's as if we're listening to a symphony with distinct movements, a natural composition playing on a scale of light years. What could possibly cause such a phenomenon? The leading theory points to the black hole's messy eating habits. As vast streams of gas and dust are pulled into the accretion disk, they don't fall in smoothly. The material clumps and jostles, creating immense pressure and turbulence. One compelling idea is that a smaller, dense object, like a neutron star or even another smaller black hole, is in a very tight, unstable orbit within the disk. With each close pass, it plows through the superheated gas, sending a powerful, rhythmic shudder through the entire structure. This regular disturbance would then be imprinted onto the gravitational waves it emits, like a drum being struck at precise intervals by a cosmic mallet. However, the sheer complexity of the patterns has pushed some scientists to consider far more exotic explanations. One fascinating possibility involves cosmic strings. These are hypothetical, one-dimensional defects in the fabric of space-time, relics from the universe's earliest moments, thinner than an atom but possessing immense density. If one of these strings were to vibrate near the event horizon of the black hole, its oscillations could, in theory, generate the intricate, multi-frequency gravitational wave patterns we observe. It would be like a violin string being bowed by the immense gravity of the black hole, producing a celestial tune that has been playing for billions of years. To truly appreciate this, let's listen to a simulation. Pause for a simulated audio clip. What you're hearing is a sonification of the actual data. That deep, pulsing tone is the heartbeat of the black hole, while the rising and falling chimes represent the complex interactions happening just outside the point of no return. This isn't just a scientific curiosity, it's a revolutionary tool. By analyzing this music, astronomers can probe the environment around a black hole with unprecedented detail, learning about its mass, spin, and the physics of its accretion disk in ways that light-based astronomy alone could never allow. The singing black hole of NGC 262 is more than a marvel. It's a new language through which the cosmos is speaking to us, revealing the hidden dynamics of the most extreme environments in existence. And just when we thought the galaxy's wonders couldn't become more surreal, our journey takes us to a star system that seems plucked from the realm of fantasy, a family of worlds known collectively as the crystal planets. Orbiting a young, intensely hot white star, these aren't the familiar rocky or gaseous worlds of our own solar system. Instead, they are glittering spheres of near-pure crystal, their surfaces and interiors composed of vast, transparent lattices that catch the starlight and fracture it into breathtaking, permanent rainbows. Imagine a world where the very ground beneath your feet is a single, massive gemstone, with mountain ranges that are not dull rock, but towering, faceted structures refracting light in every direction and canyons that glow with an internal, prismatic fire. The formation of such impossible worlds hinges on a perfect and incredibly violent storm of geological circumstances. In our own solar system, conditions were right for silicon and oxygen to combine into common silicate rocks, forming the basis of planets like Earth. But in this distant system, the protoplanetary disk, the cloud of dust and gas from which the planets formed, was extraordinarily rich in specific elements like carbon, aluminum, and beryllium. Under the immense gravitational pressure of a planet's formation, combined with colossal heat from both accretion and the nearby star, these elements were forced into exotic mineral forms. Think of it as a cosmic forge operating at a far higher temperature and pressure than what shaped our own world. Here, carbon was compressed not into graphite, but into vast diamond-like structures. Aluminum and oxygen fused into enormous sapphire crystals, and beryllium compounds created otherworldly mineral formations like alexandrite. The result was not a planet with scattered crystal deposits, but a world that is, from its core to its upper mantle, a single, continuous crystalline matrix. This leads us to one of the most exciting questions raised by these glittering orbs. Could life exist there? We have to completely redefine our understanding of what life could be. On Earth, life is carbon-based and relies on water as a solvent. On a crystalline world, biology as we know it is impossible. However, some astrobiologists speculate that the crystals themselves could form a kind of inorganic information processing matrix. Tiny fractures and imperfections within the crystal lattice, constantly shifting due to tectonic stresses and bathed in the star's energy, could theoretically create complex, self-organizing patterns. These patterns might not be life as we breathe and eat, but they could be a form of sentience built from light and structured silicon, a slow, geological intelligence that thinks over millennia, its consciousness woven into the very fabric of the planet. Alternatively, the immense internal energies generated by piezoelectric effects where the crystals generate electrical charges when stressed could provide a power source for entirely unknown forms of energy-based organisms. Visualizing these worlds is key to understanding their majesty. Picture a CGI flyover of the largest of these crystal planets. As your viewpoint descends through a thin atmosphere, the surface below isn't a patchwork of colors, but a single, seamless expanse of polished crystal, gleaming with a deep blue hue. Sunlight doesn't simply illuminate the landscape. It penetrates it, traveling for miles through the transparent crust and illuminating subterranean caverns with a soft, ethereal glow. During the system's day, the entire world becomes a colossal disco ball, throwing off brilliant, shifting spears of colored light into the void. At night, the surface might still shimmer with a faint, internal luminescence, a remnant of the stellar energy absorbed during the day. The scientific drive to study these worlds up close is overwhelming. Future missions equipped with advanced spectroscopic sensors and ruggedized landers could one day attempt to touch down on these fragile, diamond-hard surfaces. A lander wouldn't carry a traditional drill, but rather a laser cutter designed to delicately sample the crystalline structure without causing catastrophic fractures. The primary goal would be to analyze the crystal's isotopic ratios and internal imperfections, which would act as a historical record, telling us not only the planet's age but the precise conditions of the early solar system. Furthermore, by listening for subtle acoustic vibrations within the planet, a technique called planetary seismology, we could map its internal structure and perhaps even detect the slow, rhythmic pulses of energy that some theories suggest could be a sign of that exotic crystalline consciousness. The crystal planets challenge our definitions of a world, of geology, and even of life itself, proving that the universe's capacity for wonder is truly limitless. Leaving behind the glittering crystal worlds, we now encounter a phenomenon that challenges our most fundamental experience of reality, the passage of time itself. Nestled within a densely packed region of NGC 262 is a star cluster that astronomers have designated as the Chronos anomaly, a place where the universe's clock seems to be broken. Observations here reveal something profoundly unsettling. The processes of stellar life and death do not unfold at a single universal rate. In one part of the cluster, stars evolve and expire at a pace we would consider normal, while in another, just a few light years away, their identical twins appear to age in extreme slow motion, as if time has become thick and sluggish. This isn't a measurement error or an illusion. It is a stunning, real-world demonstration of Einstein's theory of general relativity playing out on a colossal scale. The key to understanding this lies in the immense gravitational forces at work. Einstein revealed that gravity is not just a force that pulls on objects, but a curvature in the very fabric of spacetime. The stronger the gravity, the more spacetime is warped, and this warping directly affects the flow of time. Think of spacetime as a vast, stretchy rubber sheet. Place a heavy bowling ball in the center, and it creates a deep indentation. Now imagine rolling two identical marbles across this sheet, one close to the bowling ball and one far away. The marble near the heavy object has to travel through more severely curved space, which from our perspective looks like it's moving slower. This is the essence of gravitational time dilation. Time itself runs slower in stronger gravitational fields. In the Chronos anomaly, the gravitational field is created by an incredibly dense knot of stars, including a central supermassive black hole and thousands of neutron stars packed into a relatively small volume. This creates a gravity well so deep that time near the center ticks significantly slower than time at the cluster's outer edges. We can observe this mind-bending effect directly by watching the stars themselves. Astronomers use certain types of stars as cosmic clocks, Cepheid variable stars, for instance, pulsate with a regular rhythm that is directly tied to their intrinsic brightness. By monitoring these stars throughout the Kronos anomaly, a clear pattern emerges. The Cepheids orbiting near the dense core pulsate at a measurably slower rate than their counterparts in the cluster's outskirts. Furthermore, the aging process of massive, short-lived stars tells the same story. A massive blue giant star that should explode as a supernova after only a few million years will appear to live much longer from our distant vantage point if it resides deep within the cluster's gravitational heart. Its entire life cycle, from fiery birth to cataclysmic death, is stretched out from our perspective, a dramatic slowdown orchestrated by gravity itself. To visualize this, picture a simple diagram. A cluster of stars is shown with a color gradient from yellow at the edges to deep red at the center. A clock face is superimposed over each region. On the outskirts, the clock ticks at a normal, steady pace, but as we move inward, the ticks become further apart until at the very core, the second hand seems to crawl. This illustrates the relativistic gradient of time, a slope of temporal flow created by the collective mass of the cluster. It's as if the entire cluster is a cosmic hill, and time runs faster at the top and slower at the bottom. For any hypothetical civilization living on a world near the core, a single generation might pass while on a world at the edge. Centuries of history unfold. Their astronomy would be a constant reminder that the universe operates on more than one timescale. This has staggering implications for the future of interstellar travel and our understanding of cosmology. For spacefarers, navigating such a region would be a navigational and biological nightmare. A ship spending what feels like a year exploring the core would return to the wider galaxy to find that decades or even centuries had passed for everyone they ever knew. The cluster acts as a natural time machine, not into the past but into the future of the surrounding galaxy. On a grander scale, the Kronos anomaly serves as a unique natural laboratory. It allows us to test the limits of general relativity under conditions of extreme gravity that we could never recreate on Earth. By meticulously mapping the time dilation across the cluster, we can probe the distribution of its dark matter, a mysterious substance that contributes significantly to the gravity well but remains invisible. The way time bends tells us precisely how much mass is there, visible or not, offering a new tool to unravel one of cosmology's greatest mysteries. This cluster is more than a collection of stars. It is a dynamic, four-dimensional sculpture carved from spacetime itself, demonstrating with beautiful, terrifying clarity that time is not an absolute river, but a fluid that flows at different speeds throughout the cosmos. But what if the most spectacular light show in the cosmos was completely invisible to our eyes? As we journey further into the enigmas of NGC 262, we come across a planet where the sky itself is alive with a secret performance, a phenomenon known as the ghostly aurora. Imagine a world where the entire atmosphere, from pole to pole, is constantly painted with colossal, swirling ribbons of light. But this isn't the familiar green and red of Earth's northern lights. This aurora radiates in wavelengths far beyond what human vision can perceive, blazing brilliantly only in the high-energy realms of extreme ultraviolet and X-rays. It is a permanent, planet-spanning storm of light that remains utterly hidden, a ghostly spectacle revealed only when we look through the electronic eyes of our most advanced space telescopes. The sheer scale and power of this aurora are almost incomprehensible. On Earth, our beautiful auroras are a transient gift from the sun, triggered when solar wind particles are channeled by our planet's magnetic field toward the poles, colliding with atmospheric gases. The ghostly aurora, however, dwarfs this completely. It doesn't just dance near the poles, it envelops the entire planet in a frenetic, shimmering shroud. The energy required to sustain such a global display is millions of times greater than anything in our solar system, suggesting this world is subject to an astronomical particle accelerator of unimaginable ferocity. The primary driver is almost certainly the planet's parent star, a highly active red dwarf prone to violent flares and coronal mass ejections. But the real key lies in the planet's own magnetic field, which is thought to be extraordinarily powerful and complex, perhaps even multipolar, with several north and south poles creating a tangled web of magnetic pathways that trap and accelerate charged particles across the entire globe. This leads us to the central mystery: what exactly is glowing? The light we see in our translated images comes from atoms in the upper atmosphere being struck by these high-energy particles and becoming excited. However, the specific wavelengths detected intense ultraviolet and even soft X-rays point to a far more violent process than the gentle glow of oxygen and nitrogen we see on Earth. The particles hitting this planet's atmosphere must be traveling at a significant fraction of the speed of light, possessing enough energy to strip electrons from even heavy, stable atoms. This has forced scientists to consider the presence of unknown particles in the stellar wind or an exotic atmospheric composition. Perhaps the planet's air is rich in noble gases like neon or argon, which emit light in these extreme wavelengths when energized. Or, more intriguingly, the magnetic field itself could be accelerating normal particles to such ludicrous speeds that they generate X-rays upon impact, a process usually seen near neutron stars or black holes. To truly appreciate the hidden beauty of this phenomenon, we must rely on scientific visualization. By combining data from X-ray and ultraviolet telescopes, artists and scientists can create a composite image that translates the invisible into a vibrant false color display. In this visualization, the entire planet would be encased in a dynamic, fiery halo. Swirls of brilliant magenta and cyan, representing the most energetic X-rays, would writhe around the magnetic poles, while vast, ethereal curtains of deep blue, signifying intense ultraviolet light, would stretch across the equatorial regions. The entire world would look like it was caught inside a colossal, slowly churning neon nebula, a vision of terrifying and beautiful violence that plays out in complete silence and invisibility. The existence of the ghostly aurora has profound implications for the search for habitable worlds. This planet is almost certainly located within its star's theoretical habitable zone, the region where temperatures could allow for liquid water. However, the constant bombardment of high-energy radiation that creates the aurora would sterilize the surface, making life as we know it impossible. It serves as a critical reminder that a planet's position is not enough. Its magnetic shield and the temperament of its star are equally vital. For astrobiologists, this phenomenon acts as a cosmic beacon, flagging worlds that are visually stunning but biologically forbidding. At the same time, it sparks a fascinating hypothetical question. Could there be life forms that not only withstand such radiation but actually feed on it? While purely speculative, the idea of subsurface organisms that use the constant energy input from this celestial light show, much like deep-sea vent life on Earth uses chemical energy, is a thrilling thought. The ghostly aurora is a masterpiece of cosmic forces, a brilliant warning sign, and a testament to the fact that the universe's most awe-inspiring art is often painted in colors we cannot see. Now we venture into the domain of the deeply bizarre, where the laws of physics as we understand them seem not just bent but broken. Our sixth phenomenon introduces us to a stellar pair known as the quantum-entangled binary stars. Picture two massive suns separated by a gulf of 3 light-years, a distance so vast it would take a beam of light, the fastest thing in the universe, 3 full years to travel from one to the other. According to the bedrock principle of Einstein's relativity, nothing can travel faster than light, meaning any influence or signal between these stars should take at least 3 years to make the journey. Yet the data tells a different, almost impossible story. Observations show that when one star erupts in a colossal flare, its twin does the same, not 3 years later, but in perfect, instantaneous synchronization. It's as if the two stars share a single consciousness, linked by an invisible thread that defies the cosmic speed limit. This spooky action at a distance, as Einstein himself once skeptically described quantum entanglement, is something physicists have demonstrated in laboratories with tiny particles like electrons. When two particles become entangled, they share a single quantum state. Measuring one particle, say, finding its spin is up, instantly forces the other particle, no matter how far away, into the opposite down spin. This connection is immediate, transcending space. To witness what appears to be this same principle operating on a stellar scale, with objects billions of times more massive and complex than a single electron, is nothing short of revolutionary. The evidence for this connection is etched into the light we collect from them. High-precision spectrographs reveal that their light spectra shift in perfect, mirrored unison, indicating simultaneous changes in temperature and magnetic field strength. X-ray and radio telescopes capture flares erupting in absolute lockstep, a coordinated dance of stellar violence that has no conventional explanation. How could such a thing be possible? One natural explanation posits that these two stars were born from the same dense knot of gas and dust in the very recent past, astronomically speaking. In their earliest moments, they were so close that their subatomic particles could have become quantum entangled on a fundamental level. As the stars drifted apart, this primordial connection may have been preserved, somehow scaling up to govern their macroscopic behavior. It's a staggering idea that the furious nuclear furnace of a star, with its immense gravity and chaotic plasma, could be governed by the delicate, probabilistic rules of the quantum world. If true, it would force a complete rewriting of astrophysics, bridging the gap between the infinitesimally small and the astronomically large in a way we've never seen before. To make this relatable, consider an analogy far removed from the cosmos. Imagine you have a pair of magic coins, each given to a friend on opposite sides of the Earth. You flip your coin and it comes up heads. At that exact instant, without any signal or communication, your friend's coin also flips itself and lands on tails. Every single time. That is the essence of quantum entanglement. Now, scale that up from a coin to a raging, million-mile-wide ball of fire, and you begin to grasp the profound weirdness of these binary stars. Their connection suggests that the universe at its most fundamental level is deeply, holistically interconnected in ways that our everyday experience of time and space completely hides from us. Given the extreme improbability of this occurring naturally, a more speculative line of inquiry must be considered. Could we be looking at a signature of technology? The precision of the synchronization is so exact that some theorists have proposed these stars might not be natural at all, but rather contained or manipulated by a civilization of unimaginable advancement. One hypothetical concept involves a Dyson sphere-like structure, but far more sophisticated, a quantum-linked network. An ultra-advanced culture might use the stars as power generators or communication nodes, entangling them artificially to create an instantaneous, unhackable information network spanning light years. The synchronized flares wouldn't be random stellar activity, but purposeful data pulses in a galaxy-wide internet. While this idea resides firmly in the realm of speculation, its mere plausibility highlights how profoundly this phenomenon challenges our grasp of what is possible. The quantum-entangled binary stars present us with two equally mind-bending possibilities. Either we are witnessing a natural quantum miracle that redefines physics, or we are staring at the workings of a technology so advanced it appears to us as magic. Following the cosmic threads of quantum entanglement, we now turn our gaze to the seemingly empty spaces between the stars, where another profound mystery is unfolding. Drifting through the vast spiral arms of NGC 262 are immense, wispy clouds of interstellar dust, but these are far from the passive, floating grit we might imagine. These are the living dust clouds, and they exhibit a behavior that is unsettlingly dynamic. long-term observations reveal that these clouds don't just drift randomly on cosmic winds. They coalesce, disperse, and reform in intricate, organized patterns that mimic the purposeful movements of a swarm. They pulse and flow, at times gathering into dense, dark knots before unraveling into delicate filaments, almost as if they are breathing. This coordinated motion defies the chaotic nature of simple gas and dust clouds, suggesting there is more at work here than basic physics. When astronomers point their most sensitive spectrometers at these clouds, the data reveals a chemical composition that is as complex as the cloud's behavior. We are not looking at simple ices or silicates. Instead, the spectra are rich with the signatures of complex organic molecules, polycyclic aromatic hydrocarbons, long-chain carbon molecules, and even amino acids, the fundamental building blocks of proteins. Finding such a rich probiotic soup in the cold emptiness of interstellar space is extraordinary. It's like discovering a fully stocked kitchen in the middle of a barren desert. This has ignited a fierce debate. Are we simply witnessing the natural, if advanced, chemistry that precedes life, or could we be seeing the faint echoes of life itself? Some researchers speculate that within the protective cores of these dust grains, primitive, self-replicating molecular systems could have evolved, a form of life so alien it exists without planets, using the dust itself as its substrate and starlight as its energy. The key to their strange, coordinated movement likely lies in their interaction with the galaxy's invisible forces. Each tiny dust grain, no larger than a speck of smoke, is likely electrically charged. This allows them to become puppets of the local magnetic fields, aligning and moving along the field lines like iron filings on a sheet of paper. Furthermore, the intense radiation pressure from nearby stars pushes on the grains, and complex feedback loops between this light, the magnetic fields, and the collective charge of the entire cloud could create the swirling, pulsing patterns we observe. It's a form of natural computation where energy and fields create a system of stunning complexity. The clouds aren't alive in the conventional sense, but they may be operating as a complex system, a halfway point between inert matter and biological organization. To truly appreciate the intricate structure of this cosmic dust, we need to shift our perspective to the microscopic. Imagine a visualization that zooms in dramatically, revealing that what looks like a simple haze from a distance is actually a stunningly complex architecture. Each grain of dust is revealed to be a fractal-like structure, a delicate branching web of carbon and silicon, resembling a snowflake but built on a molecular scale. These tiny, porous structures have immense surface areas, perfect for complex chemistry to occur. In our animation, we would see these fractal grains linking together, forming chains and lattices, creating a vast, three-dimensional tapestry that floats between the stars. This isn't a chaotic dust bunny, it's a dynamic, evolving matrix of incredible complexity. The implications are so profound that they have sparked concrete plans for future interstellar missions. The most ambitious proposal involves sending a fleet of small, hyper-fast probes on a flyby mission through one of these clouds. These wouldn't be traditional rovers, but more like robotic hummingbirds equipped with microscopic sample collectors and miniature mass spectrometers. Their goal would be to gently capture individual dust grains without destroying their delicate structures and immediately analyze their chemical and isotopic makeup. The primary scientific objective is to search for molecular homochirality, a preference for left-handed or right-handed versions of molecules, which on Earth is a signature of biological processes. Finding such a bias in these clouds would be the strongest evidence yet that life, or its direct precursors, can originate in the deep void of space, forever changing our understanding of where life can begin. The living dust clouds of NGC 262 challenge our very definitions of life and environment, suggesting that the void between stars is not empty at all, but a vibrant, chemical-rich frontier where the first whispers of biology may already be stirring. Now, as we peer into the very heart of NGC 262, we find a celestial tug-of-war of epic proportions. The core of this magnificent spiral, a region packed with billions of stars, is engaged in a cosmic dance move that defies intuition. It is spinning in the exact opposite direction to the rest of the galaxy. Imagine a colossal whirlpool where the very center is churning backwards against the flow of the entire surrounding vortex. This is the reverse spin galaxy core, a phenomenon that creates a zone of immense turbulence and astrophysical violence where these two counter-rotating systems grind against one another. The most widely accepted explanation for this backward spin points to a dramatic, ancient collision. Billions of years ago, NGC 262 likely devoured a smaller companion galaxy. As this smaller galaxy was drawn in, its unique angular momentum was imprinted onto the gas and stars that merged into the central region. It's a cosmic example of stirring a cup of coffee one way and then suddenly adding a splash of cream stirred in the opposite direction. The two motions conflict, creating swirls and eddies at their boundary. Sophisticated computer simulations of galactic dynamics show that such a merger can naturally result in a stable, counter-rotating core, a fossilized record of a long-finished act of cosmic cannibalism. However, an alternative, more exotic theory suggests that powerful, precessing jets from the central supermassive black hole could have exerted enough torque over eons to gradually slow, stop, and reverse the core's original spin, like a divine hand reaching in to twist the galaxy's very heart. This clash of rotations has profound and visible consequences. The boundary between the backward spinning core and the forward spinning outer disk is a region of extreme gravitational shear. Here, vast clouds of hydrogen gas are not just compressed, they are violently wrenched and torn apart. This triggers ferocious, chaotic bursts of star formation. Unlike the orderly spiral arms where stars are born in relative calm, this turbulent frontier gives rise to massive, short-lived stellar behemoths that burn brilliantly and die young in spectacular supernova. The area is a stellar production line running at a frantic, unsustainable pace, flooding space with intense radiation and newly forged heavy elements. To visualize this, a three-dimensional model is essential. Picture NGC 262 as a flat, spinning disk of stars. Now focus on the central bulge. In our model, this core begins to glow with a different color and slowly, deliberately, rotates in the opposite direction. At the boundary, we see a visible shockwave of energy, a glowing, turbulent ring where the two opposing flows collide. Streamers of gas are shown being stretched and compressed, sparking off brilliant blue clusters of newborn stars. This dynamic model illustrates why this region is also a powerful particle accelerator. The intense magnetic fields and shock waves in this turbulent zone can accelerate protons and electrons to nearly the speed of light, creating a fountain of high-energy cosmic rays that stream out into the galactic halo, influencing the environment far beyond the core itself. Studying this reverse spin core gives us a unique window into the life story of galaxies. It confirms that galaxies are not isolated, static islands, but dynamic entities that grow and evolve through violent mergers. By analyzing the age and composition of the stars in the counter-rotating core, astronomers can effectively date the ancient collision that caused it, piecing together the galaxy's evolutionary timeline. This phenomenon in NGC 262 provides a nearby laboratory for understanding a process that is fundamental to galaxy formation across the universe. It shows us that even the most fundamental property of a galaxy, its direction of spin, can be rewritten by its history, a permanent testament to the chaotic and dramatic forces that shape the cosmos. As we chart the strange cartography of NGC 262, our journey leads us to a patch of nothingness so profound it has become a primary focus of study. In a bright arm of the galaxy, teeming with the light of millions of stars, there exists a perfect sphere of absolute darkness, a region astronomers call the light-eating void. This is not a black hole which announces its presence by violently pulling matter inward and emitting X-rays. It is not a dark nebula which merely blocks background light like a cosmic cloud. This void is something else entirely, a three-dimensional area of space that appears to absorb nearly 100% of the light, radio waves, and other radiation that enters it. It is a perfect cloak of black against a brilliant tapestry, a hole punched in the fabric of the luminous universe. The discovery of this void came not from seeing it directly, but from noticing what was missing. Astronomers were mapping a particularly luminous star cluster when they noticed a strange, circular absence of background galaxies. It was as if a giant, invisible lens was floating in space, magnifying nothing. This was the clue that pointed to gravitational lensing, one of Einstein's key predictions. The immense gravity of a massive object can bend the path of light from objects behind it, acting like a magnifying glass. But in this case, the lensing effect was bizarre. The light from galaxies directly behind the void was not being magnified or distorted, it was simply vanishing. We could see the warped light from galaxies around the edges of the void. Their images stretched into faint, luminous arcs, proving that something with tremendous gravity was there. Yet, at the center of this gravitational field, there was only an utter and complete blackness, a sinkhole for photons. This paradoxical combination, immense gravitational pull with a total lack of emissions, has forced physicists to consider explanations that sound like they are pulled from the pages of a theoretical textbook. The first and most conservative hypothesis involves a swarm of primordial black holes. These are hypothetical relics from the Big Bang itself, tiny black holes that could have formed in the universe's first moments due to dense fluctuations. If a vast cloud of these microscopic black holes clustered together, their collective gravity could produce the lensing we see, while their small individual sizes would make them inefficient at accreting gas and producing the bright accretion disks of their supermassive cousins. They would be a dark collective mass, invisible yet powerful. A more exotic idea points to a concentration of dark matter of a type we have never encountered. We know dark matter exists because of its gravitational effects, but it famously does not interact with light. What if, in this specific region, the dark matter is so incredibly dense that it forms a stable macroscopic structure? This wouldn't be a diffuse halo, but a solid-like ball of dark matter particles, a dark matter asteroid on a galactic scale. Its gravity would be immense, bending light around its edges, but with no normal matter to collide and heat up, it would remain perfectly, utterly dark. Then there is the most speculative yet fascinating possibility, a gravastar, short for gravitational vacuum star. This is a theoretical alternative to a black hole. In this model, what we think of as a singularity is replaced by a bubble of dark energy, an exotic, repulsive force generating substance that pushes outward. This bubble would be contained within a thin shell of unimaginably dense matter. From the outside, a gravastar would look very much like a black hole, bending light and possessing huge gravity. But because nothing actually falls to a central point, there would be no Hawking radiation or other emissions to detect. It would be the ultimate cosmic illusion, a void by design. The visual representation of this phenomenon is both simple and deeply unsettling. To illustrate it, we would show a vibrant star field, rich with the blues and whites of distant suns and the pink glow of nebulae. And then, right in the center, a perfect circle of pure black. Not gray, not dim, but a total absence of light. As we zoom in, we would see the telltale signs of its gravitational influence. The stars and galaxies immediately around its edge would appear to slide and warp, their light bent into a perfect ring of distorted images encircling the central nothingness. It would look like a cosmic drain, with the light of the universe flowing around its edge before disappearing into the abyss. The existence of the light-eating void places us at the very frontier of physics. It represents a clean laboratory for testing our most fundamental theories against an object that provides gravity without light, mass without substance. Every photon that disappears into its embrace is a piece of data we cannot recover, a secret the void keeps perfectly. By studying the precise way it lenses the light around its edges, we can rule out some theories and lend weight to others, slowly narrowing down the list of cosmic possibilities. It stands as a silent, dark monument to the limits of our current knowledge, a stark reminder that some of the universe's most massive and influential objects might be the very ones we cannot see at all. But our exploration of the strange would be incomplete without confronting a phenomenon that seems to actively challenge our definitions of consciousness. We now turn to the Proteus Nebula, a vast cloud of ionized gas that appears to watch, learn, and react. Unlike other nebulae that drift and evolve over millennia, Proteus transforms its shape on timescales of mere months, responding to cosmic events in its vicinity with what can only be described as purposeful adaptation. When a nearby star erupted in a supernova, releasing a devastating shockwave of radiation and particles, astronomers expected the nebula to be shredded or dramatically blown apart. Instead, something remarkable happened. As the wave approached, the nebula's tendrils retracted and its central region coiled into a dense, protective shell, significantly reducing the damage it sustained. It was a maneuver, a cosmic duck for cover, that seemed to indicate not just a reaction, but a form of anticipatory learning. The conventional physics behind this behavior is already a frontier of complexity. The Proteus Nebula is a massive plasma structure, a sea of electrically charged particles that is highly responsive to magnetic fields. Its apparent intelligence could be an emergent property of a chaotic system. Think of it as a cosmic version of a weather pattern or a flock of starlings. No single bird in a murmuration is in command, yet the collective entity moves with stunning coordination, creating complex shapes in an instant. Similarly, complex feedback loops between the nebula's internal turbulence, its own self-generated magnetic fields, and the external stimuli it receives could create a system of plasma dynamics that gives rise to these adaptive, organized patterns. The nebula's memory could be encoded in the stability of its magnetic field lines, which retain a configuration until a strong enough external force compels a restructuring, creating the illusion of learning from past experiences. This leads us directly to the profound questions posed by astrobiologists. If we were to discover a life form that was not carbon-based, not even cellular, but a planet-sized cloud of organized plasma, how would we recognize it? Our current definitions of life focus on characteristics like metabolism, growth, reproduction, and response to stimuli. The Proteus Nebula blurs these lines. It consumes energy from nearby stars, it grows and changes shape, and it certainly responds to stimuli in a complex way. Could reproduction be as simple as a magnetic filament pinching off to form a new, smaller plasma cloud? Scientists are deeply divided. Some argue this is simply a fascinating case of complex system dynamics, a natural robot following intricate physical laws. Others contend that if a system can gather information from its environment, store it, and use it to enhance its own survival, it meets a crucial criterion for a form of intelligence, however alien. To witness this behavior is to watch a cosmic Rorschach test come to life. Time-lapse imagery compiled over several years is breathtaking. We see the nebula begin as a loose, amoeba-like smear. Then, as a pulse of intense radiation from a passing comet or a distant gamma ray burst washes over it, the cloud reorganizes. Filaments of glowing gas spiral inward, forming a temporary eye-like vortex. At another point, it extends long, probing tendrils toward a neighboring star cluster, as if sampling the stellar winds. The transformations are fluid and strangely graceful, lacking the chaotic randomness we would expect from a simple gas cloud being pushed around by stellar winds. It moves with an unnerving sense of agency, a silent, sentient-seeming entity painted across light-years of space. This, of course, raises monumental ethical questions that humanity is utterly unprepared to answer. If the Proteus Nebula is in some way a living, thinking being, then our entire approach to it changes. Our standard procedure for studying a nebula involves bombarding it with every wavelength of light we have, from radio waves to X-rays, to analyze its composition. But if this entity is conscious, are we merely observing it, or are we shining a blinding spotlight into its eyes, poking and prodding it without its consent? The idea of a first contact scenario with a being that is not a little green man, but an entire ecosystem that thinks with magnetic fields and feels with currents of plasma, is both awe-inspiring and terrifying. It forces us to expand our empathy on a galactic scale, to consider that the greatest intelligences in the cosmos might not be on planets at all, but are the very structures we've always considered to be mere scenery in the theater of the universe. Moving from the silent, sentient nebula, we encounter a spectacle of raw, unbridled power, a tempest of such scale and longevity it defies earthly comprehension. On a colossal gas giant, a world many times the size of Jupiter, a single hurricane has raged without pause for what we estimate to be over 10,000 years. This is the eternal storm, a vortex of swirling clouds and supersonic winds that could easily swallow our entire planet whole, a permanent fixture in the atmosphere of a distant world that makes even the most violent weather on Earth seem like a gentle breeze. What fuels such an unending cataclysm? On our own Jupiter, the Great Red Spot is a high-pressure storm sustained primarily by the planet's own internal heat, slowly radiating out from its formation billions of years ago, combined with the complex shear forces between the planet's banded jet streams. The eternal storm, however, operates on an entirely different level of energy. The gas giant it calls home is not just large, it is a super Jupiter, a behemoth with a ferociously hot interior, still glowing from the intense pressure of its own formation and from the continuous gravitational compression of its unimaginable mass. This internal furnace drives convection on a staggering scale, forcing vast plumes of hot gas to rise from the depths, while cooler gas sinks, creating a self-perpetuating engine of atmospheric chaos. Furthermore, this world is locked in a tight, eccentric orbit with a sibling gas giant, creating immense and constantly varying tidal forces. These gravitational tugs squeeze and stretch the planet's interior, pumping additional heat into the atmosphere like bellows stoking a fire, providing a nearly limitless external energy source that our solar system storms simply do not possess. The comparison to Jupiter's Great Red Spot is both instructive and humbling. Our solar system's most famous storm is a relative toddler, likely only a few centuries old, and it has been steadily shrinking for decades. The eternal storm, by contrast, shows no signs of fading. Its size is its secret. The storm's diameter is so vast that the Coriolis effect, the same force that causes hurricanes on Earth to spin, is exponentially stronger, locking the vortex into a stable, coherent structure that is incredibly difficult for surrounding weather patterns to disrupt. It acts less like a temporary storm and more like a permanent atmospheric feature, a continent of fury carved from clouds of ammonia and water ice, with lightning flashes so powerful they momentarily outshine the system's sun. To truly grasp its majesty, we must visualize it from orbit. Imagine a spacecraft's eye view descending through the void toward the banded ochre and white of the gas giant. As we approach, a single feature dominates the entire hemisphere, a swirling, deep crimson maelstrom, its cloud tops towering hundreds of kilometers above the surrounding atmosphere. Our simulated camera plunges into the upper haze, revealing the storm's intricate structure. We fly over cloud banks the size of continents, seeing the vast, clockwise spinning vortex in its entirety, its outer bands a frenzied cascade of smaller eddies and jets. Deep within the eye, which is itself larger than Earth, we wouldn't find calm but a terrifying arena of towering thunderheads, each one illuminated from within by continuous continent-sized lightning storms, a cacophony of elemental violence that has been playing out since the dawn of human civilization. The scientific value of studying this eternal storm extends far beyond mere celestial curiosity. It serves as a supreme laboratory for understanding fluid dynamics and long-term climate stability under extreme conditions. By modeling the complex interplay of internal heat, tidal energy, and atmospheric chemistry that sustains this storm, climatologists can refine their models for Earth's own climate system, testing the limits of weather persistence and stability. The eternal storm is a natural experiment running on a grand scale, showing us just how long-lived and powerful atmospheric systems can become when provided with a sufficiently massive and energetic environment. It stands as a breathtaking monument to the dynamic, ever-changing nature of planetary atmospheres, a whirlwind that has witnessed millennia pass as mere moments in its endless, furious dance. And now we arrive at a phenomenon of profound and unsettling quiet, a cosmic library where every book has been checked out and no one is speaking. In a vibrant, star-dense arm of NGC 262, where hundreds of millions of suns should be generating a natural radio cacophony, our most sensitive listening dishes hear only a deep, pervasive silence. This is the radio silence zone, a bubble of interstellar space where the universe's background chatter suddenly cuts out, creating a perfect dead zone for communication. It's as if a celestial mute button has been pressed, leaving astronomers to wonder if they are observing a natural anomaly or something far more deliberate. The most immediate and logical explanation points to the physical properties of the space itself. This region could be filled with an exceptionally dense and ionized interstellar medium, a thick fog of charged particles. Radio waves, which are a form of long-wavelength light, struggle to pass through such an environment. The charged particles in this cosmic haze would absorb or scatter the radio emissions from the stars and any potential civilizations within the zone, effectively trapping them. It would be like trying to shout through a soundproof wall. The sound is generated, but it cannot travel to our ears. Another natural possibility involves powerful magnetic fields that permeate the area, fields so intense that they disrupt and distort the coherent propagation of radio signals, twisting them into unrecognizable noise before they can escape the zone's boundary. This would be a natural, albeit extreme, form of cosmic interference. However, the sheer totality of the silence has forced the scientific community to entertain a more provocative idea: targeted jamming. What if the silence isn't a natural barrier but a constructed one? An advanced civilization, perhaps one that values its privacy or seeks to avoid contact with lesser developed species, could be employing technology to blanket the entire sector in a neutralizing field. This wouldn't require magic, just a highly advanced application of physics. They could be using phased arrays of transmitters to broadcast out-of-phase anti-noise that cancels out all other radio frequencies, creating a bubble of perfect destructive interference. Alternatively, they might have discovered a more efficient means of communication that doesn't leak radio waves into space at all, like using modulated neutrino streams or quantum entanglement, leaving their region of space unnaturally quiet to our primitive listening methods. The silence in this scenario is not an absence of activity, but a signature of a technology so sophisticated it has learned to hide its own emissions. This dead zone presents a monumental challenge and a source of existential anxiety for projects like the Search for Extraterrestrial Intelligence, or SETI. For decades, SETI has been predicated on the idea that intelligent species will, either intentionally or accidentally, leak radio signals into the cosmos. We've been scanning the heavens, hoping to catch a whisper of conversation. The radio silence zone turns this assumption on its head. It forces us to confront the terrifying possibility of the zoo hypothesis or the forest hypothesis, the idea that advanced civilizations are out there, but they are deliberately remaining quiet, either observing us like animals in a preserve or hiding from us and from each other like prey in a cosmic forest. The greatest fear isn't that we are alone, it's that the galaxy is teeming with life, but a galactic rule of radio silence is in effect, and we are the only ones who haven't received the memo. Our own frantic broadcasting into the void might not be a friendly hello, but a naive and potentially dangerous breach of protocol. To visualize this mysterious void, we can create a dynamic map of the galaxy. Imagine a standard chart of NGC 262, glowing with points of light representing stars and nebulae. Then we overlay the data from our radio telescopes. The entire galaxy shimmers with a faint, omnipresent radio glow, the combined hum of countless stellar winds and natural mazes. But in one specific sector, that glow abruptly vanishes, replaced by a perfectly defined dark sphere. It looks like a hole punched in the radio sky. To illustrate how signals behave, we can animate a simple radio wave, represented as a pulsating sphere expanding outward from a star inside the zone. As the wavefront reaches the boundary of the dead zone, it doesn't just fade. It violently fragments and dissipates, as if hitting an invisible, spongy barrier that soaks up every last vibration. This stark visual drives home the point that something inside that zone is either absorbing or actively suppressing the most basic form of cosmic communication, a mystery that stands as a silent, profound question mark in our quest to find our place in the universe. Just when we think we have a handle on the clockwork motions of the cosmos, NGC 262 presents us with a celestial rebellion. Among its starfields, we find a group of renegade comets that appear to be ignoring the universe's most fundamental rulebook. These are the gravity-defying comets, and their movements are so bizarre they seem to mock the elegant orbital dance described by Kepler centuries ago. Imagine a comet not swinging in a graceful, elliptical arc around a star, but instead zipping along in a perfectly straight line or executing a sharp 90-degree turn as if it's navigating an invisible cosmic highway. This isn't science fiction, it's a documented anomaly that has astronomers scrambling for an explanation, forcing us to reconsider what we know about motion on the grandest scales. To understand just how strange this is, we need to revisit the basics of orbital mechanics. Kepler's laws, and later Newton's and Einstein's refinements, tell us that any object moving through space under the influence of gravity must follow a path that is a conic section, an ellipse, a parabola, or a hyperbola. The gravitational pull of stars, planets, and even the galaxy itself acts as an invisible hand, constantly curving the trajectory of smaller bodies. A comet's beautiful tail is always a testament to this curvature, a signature of its journey around a gravitational anchor. The comets in NGC 262, however, are drawing lines on the celestial map instead of curves. Long-term tracking data shows them moving from point A to point B with no discernible arc, or suddenly and abruptly changing direction without any visible source of propulsion. It's as if they have their own steering mechanism, allowing them to bypass the gravitational influences that govern every other object we've ever observed. Naturally, the first instinct is to look for a conventional force that could be propelling them. On a normal comet, jets of gas and dust erupt from its surface as it's heated by a star, acting like tiny, uneven rocket engines that can slightly alter its course. Solar wind, the stream of charged particles from a star, can also exert a small push. But when astronomers crunched the numbers, they found these forces to be woefully inadequate. The momentum required to produce the straight-line motion or sharp turns we see would require jet activity thousands of times more powerful than anything possible from a comet's nucleus. We would see a colossal outburst of outgassing, a temporary transformation into a small star, and yet these comets show no such activity. They are cold, dark, and seemingly inert, even as they perform their impossible maneuvers. This conclusively rules out solar winds and natural jets, leaving us with a profound physical mystery. One of the most compelling theoretical explanations pulls in the universe's most mysterious component, dark matter. We know dark matter exists because of its gravitational effects, but it famously doesn't interact with light or normal matter in any other way we can easily detect. However, what if in this specific region of NGC 262, the dark matter is not evenly distributed but clumped into incredibly dense, invisible structures? Picture an unseen network of dark matter filaments like cosmic spiderwebs woven through the galaxy. A comet entering one of these filaments might experience its gravity not as a pull from a single point, but as a uniform force along a straight line, effectively surfing the filament and following its path. The sharp angular turns could occur at the junctions where these invisible filaments meet, as the comet's trajectory is instantly redirected from one gravitational guide rail to another. It's a theoretical long shot, but it provides a potential framework for motion that appears to defy point source gravity. Another, far more speculative line of thinking leads us to the possibility of artificial propulsion. If every known natural force has been ruled out, we are compelled to ask if these objects are natural at all. Could they be probes or vessels of some kind? The precision of their straight-line paths and the crisp nature of their directional changes are highly suggestive of controlled thrust. An advanced interstellar civilization might use such vehicles for long-range survey missions, their navigation systems calculating paths that are energetically efficient, great straight lines between points of interest, rather than being slave to the gravitational hills and valleys of star systems. The comet's dark, non-emitting nature would be perfect for stealth, allowing them to move through the galaxy unnoticed by all but the most persistent observers who happen to notice the anomaly in their motion. While this idea resides at the farthest edge of scientific speculation, its value lies in forcing us to confront the limits of our understanding and to consider that some phenomena might not have a natural explanation at all. Visualizing their paths is key to grasping the sheer oddity of these objects. An animated orbital diagram is essential here. We would first see a standard solar system model with planets tracing smooth, elliptical orbits around a central star. Then we'd introduce one of these strange comets. Its path would be represented by a stark, bright line, slicing straight across the orderly curves of the planetary orbits, completely indifferent to the star's gravitational dominance. In another sequence, we'd watch a comet approach a large planet. Instead of being slingshot around it in a graceful arc, as any natural object would be, the comet's path would kink sharply, changing direction almost instantaneously as if it bounced off an invisible wall. This side-by-side comparison makes the violation of Kepler's laws visually undeniable and deeply unsettling. The origins of these comets are as mysterious as their propulsion. Are they native to NGC 262, or are they interlopers from the void between galaxies? Their trajectories don't point back to any known stellar nursery or Oort cloud analog within the galaxy. Some of their paths seem to originate from deep intergalactic space, suggesting they could be travelers on an unimaginable voyage, using NGC 262 as a waypoint. If they are artificial, their origin could be anywhere. If they are natural, their existence implies a form of physics we have not yet discovered, a set of rules that allows for gravity-free motion on a cosmic scale. They stand as silent, moving contradictions to our models of the universe, challenging us to look deeper and question harder, reminding us that for every law we write, the cosmos may have an exception waiting to be discovered. After witnessing the unnerving silence of a dead radio zone and the physics-defying paths of rogue comets, we now arrive at a phenomenon that feels almost like a welcoming beacon in the dark, a symphony of light playing out across a family of worlds. Circling a serene, ringed gas giant, several moons do not merely reflect the light of their distant sun, they generate their own. These are the bioluminescent moons, and their surfaces, or perhaps their subsurface oceans, pulse and shimmer with a soft internal radiance. Seen through standard optical telescopes, they appear as faint gray orbs. But when we switch our view to the infrared and specific narrowbands of the visible spectrum, these worlds ignite with color, revealing intricate, shifting patterns of light that cover their globes in vast, living tapestries. The source of this light is the central mystery, and the most thrilling possibility points directly to biology. On our own planet, in the crushing darkness of the deep ocean, life has mastered the art of bioluminescence. Creatures like the anglerfish use chemical reactions to create lures, while jellyfish pulse with light as a warning or a form of communication. The ecosystems on these moons could be operating on a similar principle, but on a planetary scale. Imagine vast fungal forests covering a moon's surface, their mycelial networks glowing to distribute energy or signal across continents. Or picture a global ocean beneath a thick shell of ice, where every drop of water teems with microscopic organisms that flash in coordinated patterns, turning the entire subsurface into a swirling, galaxy-like display visible through cracks in the icy crust. The energy for this light wouldn't come from sunlight, but from the moon's internal heat, from chemical vents on the ocean floor, or from the tidal forces exerted by the giant planet they orbit, creating a perpetual, gentle energy source for life to harness. These moons provide the perfect environments for such ecosystems to flourish. One of the most promising candidates is a moon with a thick, hydrocarbon-rich atmosphere and a surface dotted with lakes of liquid methane and ethane. In this frigid landscape, life would need to rely on chemistry rather than water, and bioluminescence could be a fundamental tool for survival in the perpetual haze. Another moon likely has a massive, global subsurface ocean of liquid water, kept warm by constant gravitational kneading from its parent planet. In this dark, aquatic world, light would be the primary sense. Predators might use sudden flashes to stun prey, while entire schools of larger organisms could use complex light patterns for social interaction, creating a culture of light that we are only just beginning to detect from light years away. The sheer scale of the glow covering entire hemispheres suggests that the bioluminescence is not just an accessory for a few species, but the foundational language of the ecosystem itself. To truly appreciate the beauty of these worlds, we must turn to the artist's canvas. A visualization from the surface of one of these moons would be a scene of unparalleled wonder. The sky is dominated by the colossal, ringed parent planet, hanging in a perpetual twilight sky, but the landscape itself is the true source of light. The ground, whether it's a frozen plain or a strange, spongy fungal mat, glows with a soft blue and green radiance. Towering, tree-like structures pulse with golden light along their trunks, and in the distance, vast fields of fluorescent flora ripple in waves of violet and orange, responding to some unseen environmental trigger. If the moon has surface liquids, imagine a sea of glowing methane, where waves break on the shore in bursts of incandescent foam. It is a world that has turned itself into a lantern, a self-illuminating oasis in the cold void of space. The discovery of the bioluminescent moons has instantly made them the prime target for the next generation of astrobiology missions. While a physical mission is still a dream for the future, the planning stages are incredibly advanced. The proposed mission, often called the Starlight Surveyor, would not be a single rover but a network of small, hardy orbiters. These probes would be equipped with hyperspectral imagers, capable of discerning the finest details of the light patterns, mapping their changes over time to decipher if they contain repeating sequences or complex structures that could indicate communication. The ultimate goal would be to look for something akin to a syntax in the light, a grammar of flashes and fades that would be the strongest possible evidence for not just life but intelligence. The mere existence of these glowing worlds fundamentally shifts the search for life from looking for passive chemical signatures to actively looking for complex dynamic signals. They stand as a breathtaking reminder that life, if it exists out there, may not be hiding in the shadows, but could be broadcasting its presence across the galaxy in the most beautiful language of all, light itself. But if we pull back our perspective even further, looking at NGC 262 not as an isolated island but as part of a grander community, we see a pattern emerging that connects the entire cosmic neighborhood. Stretching between this galaxy and its companions are vast, luminous bridges, colossal filaments of energy and matter that form the backbone of the universe itself. This is the cosmic web, the fundamental architecture upon which all galaxies are built, and in the region surrounding NGC 262, these filaments are not just faint theoretical structures. They are unusually bright, brilliantly illuminated, and startlingly organized, revealing the hidden skeleton of the cosmos in unprecedented detail. To understand what we're seeing, we must first grasp the composition of these cosmic arteries. The primary component is a superheated, incredibly thin gas known as the WIM, which stands for the warm-hot intergalactic medium. This isn't a gas you could breathe. It's a plasma, a seething soup of protons and electrons with temperatures reaching into the millions of degrees. We can detect this gas because its immense heat causes it to glow faintly in X-rays, and when we point our most powerful space telescopes at these filaments, they light up like neon signs against the blackness of space. But the hot gas alone cannot account for the structure we observe. The true framework, the gravitational glue that holds these filaments together and gives them their defined, thread-like shape, is dark matter. This invisible substance forms an underlying scaffold, a cosmic trellis upon which the ordinary matter condenses and flows. The bright, X-ray glowing gas is simply tracing out the contours of this much larger, unseen dark matter foundation, revealing its presence indirectly. These filaments are not passive structures, they are dynamic conduits, the universe's superhighways for matter and energy. For billions of years, they have been channeling fresh fuel, streams of pristine hydrogen and helium gas from the emptier voids of space directly into the waiting gravitational pull of galaxies like NGC 262. This constant, gentle inflow is what allows galaxies to continue forming new stars long after their initial birth. It's a cosmic delivery system, ensuring that galactic cities don't run out of the raw materials needed to build new stellar generations. Furthermore, these filaments also channel more violent forms of energy. When a supernova explodes in one galaxy or a quasar ignites in another, the shockwaves and radiation can travel along these pre-existing pathways, influencing star formation rates and the intergalactic environment in neighboring galaxies millions of light-years away. The cosmic web turns a collection of isolated islands into an interconnected, communicating metropolis. The best way to visualize this immense structure is through the use of sophisticated supercomputer simulations. Picture a visualization that begins with a view of the entire local universe, with galaxies represented as tiny points of light. Then, as the simulation runs, we see how dark matter, under its own gravity, collapses first into an intricate, three-dimensional spiderweb. This web looks like the frothy, filamentary structure of a sponge, with vast empty bubbles or voids, surrounded by dense walls and long, connecting threads. The ordinary matter, the gas, then follows this dark matter blueprint, flowing into the filaments and pooling at the intersections, which is where the great clusters and superclusters of galaxies form. Seeing this simulation unfold makes it clear that NGC 262 did not form in a random location. It was born at a nexus point in this cosmic web, a place where multiple filaments converged, delivering the immense amount of material needed to build a majestic spiral galaxy. Understanding these luminous filaments in NGC 262 vicinity is about more than just mapping the local neighborhood. It provides a crucial key to deciphering the entire history and fate of the cosmos. By studying their brightness and structure, cosmologists can measure the density and temperature of the intergalactic medium with unparalleled precision, testing our models of how the universe evolved from a nearly smooth soup after the Big Bang into the complex, structured web we see today. These filaments are fossils of the primordial universe, and their properties tell us about the nature of dark matter and dark energy, the two most mysterious components of reality. The unusually bright and structured filaments around NGC 262 offer a unique, close-up laboratory for studying this universal architecture, giving us a front-row seat to the processes that built everything we see, from the grandest galaxy to the smallest star. They are a vivid reminder that the universe is not a random scattering of lights, but a beautifully organized tapestry, woven together by gravity on the largest scales imaginable. Our journey now takes us into a treacherous, ever-changing labyrinth of rock and ice, an asteroid belt unlike any other in the cosmos. In most solar systems, asteroid belts are relatively stable places, with chunks of primordial material following predictable orbits for billions of years. But here in NGC 262, we find a belt in constant, chaotic flux. This is the shape-shifting asteroid belt, a region where the asteroids themselves appear to be alive, altering their forms and their paths with a frequency that defies all conventional models. Radar imaging reveals these objects not as static, cratered mountains, but as dynamic bodies that swell, shrink, and even change their fundamental shape over mere months, creating a navigational nightmare and a profound scientific puzzle. The transformations we witness are dramatic and varied. 1 month, an asteroid might be a roughly spherical body 50 kilometers across. 6 months later, the same object, tracked by its unique spectral signature, has elongated into a cigar shape or flattened into a bizarre pancake-like disk. Even more disconcerting are the orbital changes. Asteroids will suddenly slow down, speed up, or execute gentle but clear course corrections without any visible cause. This isn't the slow, gravitational drift we expect from minor perturbations. This is active maneuvering. To visualize this, picture a CGI time-lapse of the belt. At first, it looks like a standard field of tumbling rocks, but as the clock accelerates, the scene becomes surreal. Asteroids pulse, with sections of their surfaces bulging outward as if something is pushing from within. Some split apart gently, not from a violent collision, but almost like a cell dividing, with the two new pieces drifting slowly away from each other on new trajectories. It's a cosmic ballet of self-reorganization, a far cry from the dead, silent rocks we know from our own solar system. The most logical explanation for this incredible activity points to intense and volatile outgassing. Imagine a comet, but on a much larger scale. Many of these asteroids could be colossal, dirty snowballs packed with frozen gases like ammonia, methane, and carbon dioxide buried beneath a thin crust of dust. As they orbit their star, the slightest change in temperature, perhaps from a periodic flare or a shift in their rotation, could cause these subsurface ices to turn directly into gas. This process, called sublimation, would build up tremendous pressure until the gas finds a weak spot in the crust and erupts into space. Such a jet acts like a natural rocket engine, producing thrust. If the jet is off-center, which it almost always is, the thrust can cause the asteroid to spin, tumble, or even change its orbit. A particularly powerful or sustained outburst from one side could even reshape the entire body, explaining the dramatic morphological changes we observe. The asteroid isn't consciously changing shape. It's being sculpted by the explosive force of its own internal chemistry. However, the sheer precision of some orbital adjustments has led researchers to consider a more startling possibility: artificial modification. Could these asteroids be more than just rocks? The idea of self-replicating von Neumann probes is a staple of theoretical astroengineering. These would be robotic probes designed to travel to a star system, mine local resources like an asteroid belt, to build copies of themselves and then launch those copies to other stars. The activity we see could be the visible signature of such a process. The reshaping of the asteroids wouldn't be random outgassing, but systematic disassembly. The changes in orbit wouldn't be chaotic drifting, but precise maneuvers as these asteroids reposition themselves for more efficient mining or to avoid collisions with their counterparts. In this scenario, we aren't looking at a natural belt, but a vast automated industrial facility, a factory complex of unimaginable age and scale, silently converting raw materials into something else. While this remains a highly speculative hypothesis, it is one that must be on the table when natural explanations strain to account for the coordinated nature of the changes. This dynamic environment poses an extreme and unprecedented risk to any form of space navigation. Planning a trajectory through a normal asteroid belt is a complex but solvable problem, relying on the predictable orbits of its constituents. Navigating this shape-shifting belt would be like trying to pilot a ship through a hurricane while the islands themselves are moving. A path calculated to be safe could be blocked within days by an asteroid that has suddenly changed its course. The risks aren't just about collision. A closely passing ship could be severely damaged by an unexpected outburst of gas and debris from one of these volatile objects. This has forced a complete rethink of planetary defense strategies. Traditionally, planetary defense focuses on tracking large, stable objects on potential collision courses with inhabited worlds. But the lesson from NGC 262 is that the threat can be fluid and multifocal. A single, stable asteroid isn't the only concern. An entire population of small, unpredictable objects capable of altering their own paths presents a much more complex and insidious challenge. It suggests that early warning systems in such a system would need to be constant and real-time, capable of tracking not just positions, but also the structural integrity and outgassing potential of thousands of individual objects simultaneously. Ultimately, the shape-shifting asteroid belt forces us to see these celestial bodies not as relics of a dead past, but as active, evolving participants in their solar system. Whether driven by the furious energy of volatile ices or by the silent, purposeful work of ancient machinery, this region is a testament to the fact that chaos and order can coexist on a grand scale. It stands as a warning and a wonder, a demonstration that even the seemingly most stable and inert features of a cosmos can be teeming with hidden, transformative energy. Moving from the silent, transformative dance of the asteroid belt, we encounter a cosmic event that defies the finality of death itself. In a far-flung region of NGC 262, a star that died centuries ago continues to speak, its final moments replaying over and over again across the galaxy. This is the echoing supernova, a stellar ghost whose light refuses to fade quietly into the night. What we are witnessing is not the initial explosion, but its reflection, a series of brilliant, expanding rings of light that pulse outward from the site of the catastrophe, a celestial message on a centuries-long delay. The mechanism behind this breathtaking phenomenon is a perfect cosmic coincidence known as a light echo. When the star initially went supernova, it released an unimaginable flash of radiation in all directions. The initial pulse of light traveled directly to our telescopes, and we recorded the brilliant, sudden death of the star. However, that initial flash also illuminated vast, distant clouds of interstellar dust that were light years away from the explosion. The light from the supernova traveled out, hit these dust clouds, and then bounced off, redirecting its path toward us. Because this reflected light had to take a longer, indirect route, it arrives at our eyes years, decades, or even centuries after the original event. It's exactly like hearing an echo in a canyon. The sound of your voice travels directly to you, but a fraction of a second later, you hear it again as it bounces off a distant cliff face. In the case of this supernova, the canyon is light years across, and the echo is a wave of light that we can watch slowly expand and fade over time. this delayed broadcast provides an unprecedented scientific opportunity. For the first time, we are not limited to the single, fleeting day to point of the initial explosion. We can study the supernova's evolution in slow motion. The specific pulses observed in NGC 262's echo are particularly revealing. The first echo ring shows a signature consistent with a type Ia supernova, the kind that occurs when a white dwarf star is pushed over its mass limit. But a later, fainter echo ring carries the distinct chemical fingerprint of hydrogen, which should not be present in such an explosion. This contradiction is forcing astronomers to reconsider the textbook model for this type of stellar death. It suggests the white dwarf may have been stripping material from a giant companion star right up until the moment of detonation, and the echo is capturing different layers of the blast wave as it ripped through this stolen stellar atmosphere. We are essentially getting a three-dimensional dissection of the explosion, layer by layer, from a vantage point in time that was impossible to achieve until now. To visualize this, a time-lapse sequence is essential. Imagine a dark patch of space. Suddenly, a central point flashes with blinding intensity, the original supernova event captured in historical data. Then the screen goes dark for a moment. A year later, a perfect, faint ring of light appears, centered on the blast site but now several light months across. Year after year, we watch as this ring expands, growing fainter and larger, like a ripple on a pond. Then a second inner ring appears, followed by a third. Each one represents light that took a different path, bouncing off a dust cloud at a different distance. The result is a series of glowing, concentric shells, each one a snapshot of the supernova's light from a different moment in its brief, violent life. This phenomenon connects us directly to our own astronomical history. In our own galaxy, the supernova observed by Johannes Kepler in 1604 also produced a light echo, which was rediscovered by modern telescopes in 2008. Seeing those faint, reflected rings from an explosion witnessed over 4 centuries ago gave us a second chance to analyze that event with 21st century technology. The echoing supernova in NGC 262 offers the same gift but on a far grander scale. By analyzing the spectrum of each light echo ring, we can effectively re-observe the explosion again and again, measuring its temperature, its chemical composition, and the velocity of its expanding shockwave at multiple points in time. This turns a single, catastrophic moment into an enduring data stream, a lecture from a dead star that continues to teach us about the violent forces that shape the universe. Yet as we ponder the silent industry of asteroids and the echoing voices of dead stars, we must now confront a discovery that challenges a law of physics so fundamental it is written into every magnet you have ever held. Within the swirling arms of NGC 262, our instruments have detected something that should not exist: regions of space where magnetic fields behave as if they are generated by isolated north poles or isolated south poles all on their own. We call these hypothetical particles magnetic monopoles, and finding evidence for them is like finding a piece of electricity that is only positive or only negative, a discovery that would shatter a cornerstone of modern physics. To understand why this is so revolutionary, you need to think about the magnets in your own life. Every simple bar magnet, no matter how small, always has 2 poles. If you break it in half, you do not get a separate north piece and a separate south piece. Instead, you get 2 smaller magnets, each with its own north and south pole. This duality is a fundamental rule of electromagnetism, described by James Clerk Maxwell's equations in the 1800s. The equations themselves seem to suggest that isolated magnetic poles should be possible, symmetry with electric charges, where you can have a positive proton or a negative electron all by itself. Yet, despite over a century of searching in particle accelerators and cosmic rays, no one has ever definitively found a magnetic monopole. Their existence remains one of the great unfulfilled predictions of theoretical physics. So what are we actually seeing in NGC 262? Our telescopes are not directly imaging a particle. Instead, we are mapping the galaxy's magnetic field in unprecedented detail. And in several distinct regions, the field lines do not form the closed loops we expect. Normally, magnetic field lines must always form continuous loops emanating from a north pole and returning to a south pole. In these anomalous zones, however, the field lines appear to radiate outward from a single point, like the electric field lines around a solitary proton, or stream inward toward a point, like lines converging on an electron. They are open, not closed. This is the signature of a monopole, a source or a sink for magnetic field lines alone. The strength of these fields is immense, suggesting that if a particle is responsible, it would be extraordinarily massive and powerful, a relic potentially from the very first moments of the Big Bang. The implications of confirming their existence are staggering, touching on the very unification of the cosmos's fundamental forces. Physicists have long sought a grand unified theory, a single mathematical framework that describes the electromagnetic force, the weak nuclear force, and the strong nuclear force as different manifestations of one underlying force. The existence of magnetic monopoles is a direct prediction of many of these theories. Finding them would be the most powerful experimental validation that we are on the right track toward this theory of everything. Furthermore, these monopoles could solve another cosmic mystery. Why is the universe so magnetized? From galaxies to galaxy clusters, magnetic fields are everywhere, and their origin is poorly understood. A small number of primordial monopoles left over from the universe's infancy could have seeded these vast magnetic fields as they moved through the primordial plasma, effectively magnetizing the entire cosmos in its first moments. Let's use a simple analogy to make this abstract idea click. Think of electricity and magnetism as two different types of fluid. Electric charge is like a source of this fluid, a faucet for positive charge and a drain for negative charge. You can have just a faucet or just a drain. Magnetism, as we've always known it, is different. It's like a loop of pipe where the fluid is always circulating. You can't have a faucet without a drain because they are connected. The discovery of a magnetic monopole would be the equivalent of finding a magnetic faucet or a magnetic drain all by itself, a break in the pipe. It would mean that magnetism can be a source in its own right, finally granting it the same symmetry that electricity has enjoyed for centuries. For the field of cosmology, this would be a transformative discovery. Certain theories of the early universe predict that a specific density of these primordial monopoles should have been created in the intense heat of the Big Bang. Finding them and measuring their properties would allow us to test our models of the universe's first fractions of a second. It would be like uncovering a fossil from the first moments of time, a particle that has witnessed forces unified in a way they never are today. The magnetic monopole anomaly in NGC 262 is therefore more than a local curiosity. It is a potential window into the highest energies and the very earliest times, a single clue that could weave together the physics of the unimaginably small with the history of the impossibly large. After confronting the cosmic enigma of magnetic monopoles, we now turn our investigation to one of the most unsettling phenomena in the entire catalogue: stars that simply cease to be. Scattered throughout NGC 262 are celestial case files of suns that have vanished without any of the usual farewells. A star will be shining brightly in one set of observations, a steady point of light for centuries, and then in the next survey of the same patch of sky, it is simply gone. These are not the dramatic, explosive finales of supernova, nor do they leave behind the telltale glow of a planetary nebula or the dense corpse of a white dwarf. They are erased as if a cosmic hand reached out and switched them off, presenting us with a profound mystery of stellar mortality. The first and most conservative explanation for these disappearances is a process known as a failed supernova. In this scenario, a truly massive star, many times heavier than our own sun, reaches the end of its life. its core, no longer supported by nuclear fusion, collapses under its own immense gravity. In a normal supernova, this collapse rebounds in a titanic shockwave that blasts the star's outer layers into space, creating a brilliant days-long flash. But in a failed supernova, the core's collapse is so rapid and complete that the rebounding shockwave simply doesn't have the power to overcome the star's own gravity. Instead of exploding outward, the entire stellar structure, core and all, implodes directly into a black hole. The star winks out of the visible universe, its light extinguished as the event horizon forms and swallows it whole. It's a stellar death that occurs behind a cosmic curtain, leaving behind only the silent, dark gravity of a newborn black hole as its only epitaph. To track these celestial vanishing acts, astronomers employ a meticulous method known as difference imaging. They take a high-resolution image of a specific star field, a reference photo that serves as a baseline. Then, weeks, months, or years later, they take another image of the exact same field under identical conditions. Sophisticated software then subtracts the new image from the old one. Normally, the result is a flat, gray field, confirming that nothing has changed. But when a star has vanished, the software reveals a single, stark black dot at the location where the star once shone. This method has confirmed dozens of these disappearances across multiple galaxies, but the statistical anomaly in NGC 262 is what truly stands out. The rate at which stars are vanishing here is several times higher than in any other galaxy we have studied, suggesting that something unique about this environment is making this silent form of stellar death unnervingly common. This statistical oddity forces us to consider possibilities that stretch far beyond standard astrophysics. One fascinating, albeit speculative, idea involves wormholes. A wormhole is a theoretical tunnel through the fabric of space-time, a shortcut between two distant points. What if, under conditions we do not yet understand, a wormhole could naturally form at the core of a dying star? Instead of collapsing into a black hole, the star's entire mass could be funneled through this gateway and ejected elsewhere in the universe, or even into another universe entirely. From our perspective, the star would simply disappear, its mass and energy transported across an unimaginable distance in an instant. While this remains a concept from the pages of theoretical physics, the anomalous rate of disappearances in this galaxy provides a tantalizing, if faint, reason to keep such extraordinary ideas on the table. Then, of course, there is the most famous and provocative hypothesis of all, alien megastructures. The concept of a Dyson sphere, a vast shell constructed around a star to capture all of its energy output, was proposed as a theoretical signature of a supremely advanced civilization. If such a structure were ever built, it would gradually block the star's light from our view, causing it to fade over time. But what if the engineering was even more advanced? A civilization capable of such feats might not just capture the star's energy, but dismantle it entirely, harvesting every last atom for computational matter or some other purpose beyond our comprehension. The star wouldn't fade, it would be systematically deconstructed, its light vanishing as it is taken apart piece by piece. The unnerving frequency of these events in NGC 262 could, in this most speculative of scenarios, point to a wave of stellar harvesting underway, a galactic-scale engineering project of literally astronomical proportions. Visualizing this mystery is crucial to feeling its full weight. The most powerful way to present this is through a direct before and after comparison. We would first show a stunning, deep-field image of a rich star cluster within the galaxy, each point of light a sun like our own. One star is highlighted with a gentle, pulsing circle. Then, with a simple crossfade, we switch to the most recent image of the exact same field. The highlighted star is now gone. The circle remains, but it encircles only empty blackness. The surrounding stars are all still there, shining just as brightly, which makes the single, perfect absence at the center all the more jarring and unnatural. It creates a visceral sense of wrongness, a hole in the cosmos where a giant, powerful sun should be. The ultimate, haunting question that these vanishing stars force us to ask is not just how they disappear, but where they go. If they are collapsing directly into black holes, their matter is crushed into an infinitesimal point, lost to our universe behind an event horizon. If they are passing through wormholes, their material is on a journey to some other shore of reality, a destination we cannot even imagine. And if they are being harvested, then their substance is being repurposed, becoming the building blocks for something new, something built by intelligences whose motives and nature are completely unknown to us. Each vanished star is a silent testament to the limits of our knowledge, a cosmic disappearance that challenges our understanding of how stars live, how they die, and what other forces might be at work in the universe, quietly editing the celestial map. Leaving behind the unsettling quiet of vanished stars, we find ourselves in a region of NGC 262 where the cosmos seems to have composed its own grand symphony, not with light or gravity waves, but with motion itself. Here, entire planetary systems have orchestrated their orbits into stunningly precise mathematical ratios, creating a celestial harmony so perfect it feels composed. This is the phenomenon of harmonic orbital resonances, and while our own solar system has a few simple examples, the complexity and perfection found here are on an entirely different level, turning entire star systems into intricate gravity-bound clocks. To understand this cosmic music, we first need to grasp the basic mechanics of orbital resonance. Imagine pushing a child on a swing. If you push at just the right moment in the swing's arc at the peak of its backward motion, each small push adds a little more energy, making the child swing higher and higher. That perfect timing is a form of resonance. In space, gravity provides the push. When two orbiting bodies, like a planet and a moon, have orbital periods that form a simple integer ratio, their gravitational influences reinforce each other at the same points in their orbits. For example, in a 1-to-2 resonance, the inner planet might orbit twice for every single orbit of the outer planet. Every second time the inner planet laps the outer one, they have a close encounter, and their mutual gravity gives a consistent rhythmic tug. Over millions of years, these repeated, predictable tugs can lock the bodies into a stable, repeating pattern, much like two pendulums eventually falling into sync. What makes the resonances in NGC 262 so extraordinary is their complexity and sheer perfection. In our solar system, we see a few simple examples. Jupiter's moons Io, Europa, and Ganymede are locked in a 1-to-4 resonance. For every one orbit of Ganymede, Europa orbits twice and Io orbits 4 times. It's a beautiful, stable trio, but in one particular system within this distant galaxy, we've observed a chain of 6 planets, all locked together in a single, intricate resonant web. Their orbital periods form a precise ratio of 3-to-5 to 7-to-9 to 11-to-13. This isn't just a simple chain, it's a multi-part harmony of staggering mathematical elegance. The probability of such a complex, high-integer ratio forming naturally through the chaotic process of planetary migration and gravitational scattering is astronomically low, leading many to question if we are looking at a statistical miracle or something else entirely. These complex harmonies are not just a cosmic curiosity, they are the bedrock of the system's long-term stability. In a typical, non-resonant planetary system, gravitational tugs are random and can, over billions of years, build up to cause orbits to become eccentric, leading to close encounters, collisions, or planets being ejected into the void. But in a resonant system, the gravitational interactions are rhythmic and predictable. The planets continually give each other gentle, reinforcing kicks that keep their orbits circular and well separated. It's a self-correcting, gravitational dance where each partner knows the steps perfectly, ensuring the entire system remains balanced for eons. This particular six-planet chain is so stable that it has likely persisted with almost no change since the planets first formed, a celestial heirloom preserved in perfect working order. The most captivating way to experience this phenomenon is to not just see it but to hear it. We can translate these orbital motions into sound, creating a sonification of the cosmic dance. Imagine an animation showing the six planets as points of light orbiting their central star. As the inner, fastest planet completes an orbit, it chimes a specific musical note. The next planet, moving in its slower, resonant orbit, chimes a different, harmonious note precisely when the musical phrase repeats. As the animation progresses, we don't just see the patterns, we hear them emerge as a complex, interweaving melody. The 3:5:7 ratio becomes a haunting minor chord progression, while the higher integers add delicate, high-frequency harmonies. This isn't random noise, it's a genuine gravitational composition playing out on a scale of billions of miles, a symphony where the planets are both the musicians and the instruments, and gravity is the conductor. This breathtaking perfection inevitably leads to the profound question of origin. Could such an intricate arrangement have formed purely by chance? The leading natural theory suggests that all six planets likely formed further out in the protoplanetary disk and gradually migrated inward toward their star. As they migrated, their gravitational interactions naturally drove them into resonant chains, a common outcome in many computer simulations. However, the survival of such a long, high-integer chain is incredibly fragile. A passing star, a particularly massive asteroid impact, or the gravitational influence of a giant planet outside the chain can easily break the resonance. The fact that this one has survived suggests it has existed in a uniquely quiet stellar neighborhood, a cosmic backwater untouched by major disruptions for its entire multi-billion-year life. Yet the sheer unlikelihood has spurred more speculative lines of inquiry. Could a sufficiently advanced intelligence use planetary-scale engineering to nudge planets into such perfect harmonies? The concept isn't as far-fetched as it might seem. By strategically directing asteroids to swing past planets in a carefully calculated manner over thousands of years, the cumulative gravitational kicks could slowly fine-tune planetary orbits, guiding them into a desired resonant pattern. But why would anyone do this? The motivations could be as practical as ensuring the long-term stability of a civilization spanning multiple worlds, or as profound as creating a lasting work of art, a cosmic monument to mathematical beauty that would endure long after its creators were gone. The harmonious system would then stand as a silent, rotating testament not just to the laws of physics, but to a desire for order and beauty written across the stars themselves. Deep within the swirling architecture of NGC 262, our investigation now uncovers a feature that challenges the very nature of the universe's most dominant yet elusive substance. We have mapped a structure that astronomers call the dark matter fountain. Picture, if you will, an immense invisible geyser, a colossal jet of dark matter flowing outward from the galactic plane against the pull of gravity, as if some hidden force is pushing it away from the very galaxy it should be holding together. This isn't something we can photograph. Its presence is inferred through the most subtle of cosmic clues, the way it bends the light from galaxies billions of light years behind it. Gravitational lensing maps of this region reveal a stunning and counterintuitive shape. The dark matter, which we expect to form a smooth, spherical halo around the galaxy, is instead shooting upward in a defined, focused stream, a fountain of the invisible. To grasp the sheer strangeness of this, we need to revisit what we think we know about dark matter. Our standard model describes it as cold and collisionless. This means its particles move relatively slowly compared to the speed of light, and they barely interact with each other or with normal matter. They only feel gravity's pull. This is why dark matter naturally settles into vast, diffuse halos, providing the gravitational scaffolding upon which galaxies are built. The existence of a fountain directly contradicts this passive behavior. A fountain implies motion, direction, and an active force. It suggests that in this specific region, dark matter is not just passively collapsing under gravity. It is being acted upon, pushed, or slingshotted in a specific direction. It's as if we've discovered a river flowing uphill, defying the natural gravitational gradient that should govern its motion. So what cosmic engine could be powering this mysterious outflow? One compelling theory points to a recent colossal burst of star formation. When millions of massive stars are born in a short period, an event known as a starburst, they live fast and die young, exploding as supernova in a continuous, galaxy-shaking fireworks display. The combined force of these explosions can generate powerful galactic winds, hot streams of charged particles and radiation that blast outward from the galactic disk. The leading idea is that this torrent of normal matter could be dragging the dark matter along with it. How? Even if dark matter doesn't interact electromagnetically, it still has mass and therefore momentum. If the outflowing normal matter is dense enough, its collective gravitational pull could literally grab hold of the surrounding dark matter and tug it along, like a powerful current dragging along a submerged, invisible log. The dark matter fountain in this scenario would be a ghostly rider on a wave of stellar energy. Yet another, more exotic possibility involves the dark matter itself having properties we never anticipated. What if dark matter isn't entirely collisionless? Certain theoretical models propose a small subset of dark matter particles could interact with each other through a new, unknown force, a dark force, that operates only within their own hidden sector. In a region packed with dark matter, such interactions could build up pressure. A dramatic event like the merger of two small clumps of dark matter could then release this pent-up pressure, causing a jet of dark particles to erupt outward. This would be akin to shaking a bottle of soda and then opening it. The internal pressure forces the liquid out in a focused stream. If this is the case, the dark matter fountain is our first ever glimpse into the complex internal dynamics of the dark sector, a hidden world with its own rules and interactions. Visualizing this invisible structure requires a leap of scientific imagination. We can create a model based on the gravitational lensing data. Imagine a standard-side view of a spiral galaxy, a bright disk of stars set within a faint purple cloud representing its predicted dark matter halo. Then we introduce the anomaly. From a specific point in the galactic disk, a brilliant, concentrated jet of deep blue light erupts, pushing vertically upward through the purple halo and extending far into intergalactic space. This blue stream represents the inferred path of the dark matter fountain, its intensity showing the density of the outflow. The visualization makes it clear that this is not a gentle drift, but a focused, energetic geyser, challenging the placid image of dark matter we have held for decades. The discovery of this fountain is more than a cosmic oddity. It is a crucial key that could help us finally pinpoint the properties of dark matter. The very existence of such a structure allows us to rule out entire classes of dark matter models. For instance, the fuzzy dark matter model, which posits extremely lightweight particles, would not form such a coherent, narrow stream. It would dissipate almost instantly. The fountain-focused nature suggests the dark matter involved is cold and made of relatively heavy particles, consistent with WIMP, weakly interacting massive particles. Furthermore, by measuring the speed and density of the outflow, we can place limits on how strongly dark matter can interact with itself. This provides a direct astronomical test that complements the decades-long search for dark matter particles in underground laboratories on Earth. Experiments like LUX Zeppelin and Xeno-NNT are trying to catch a fleeting interaction between a dark matter particle and a normal atom. The properties of the dark matter fountain give these experiments a clearer target, telling them what kind of interaction cross-sections are possible in nature. It's a beautiful synergy between the cosmic and the microscopic, where a fountain of invisible matter in a distant galaxy guides the search for fundamental particles deep beneath our feet. As we journey from the invisible geysers of dark matter to the outer reaches of a star system, we encounter a world locked in a deep and permanent freeze, a planet where the very definition of a volcano has been rewritten. This is a world of ice volcanoes where the mountains themselves erupt not with fiery rock and ash, but with plumes of water, ammonia, and methane that flash freeze in the vacuum of space, creating landscapes of surreal, crystalline beauty. Imagine a vista of gleaming, white plains stretching to a horizon dominated by a colossal, sluggish fountain of slushy ice, propelling material miles into a thin, frigid sky before it falls back to the surface as a gentle snow of exotic chemicals. These are cryovolcanoes, and their existence transforms a seemingly dead, frozen ball of ice into a dynamic, geologically active world teeming with secrets. The engine that powers these cold eruptions lies deep within the planet's hidden interior, defying its icy exterior. The primary force at work is often tidal heating. This world is likely locked in a complex gravitational dance with a giant parent planet or neighboring moons. As it orbits, the immense and changing gravitational pull from these bodies constantly flexes and kneads the planet's core, much like repeatedly squeezing a rubber ball. This friction generates tremendous internal heat, enough to melt subsurface reservoirs of water and other volatile compounds, even while the surface remains frozen solid. An alternative or additional heat source comes from the slow, steady decay of radioactive elements like uranium and thorium, locked within the planet's rocky core. This radiogenic heat acts like a buried nuclear reactor, providing a constant, gentle warmth that can maintain vast, liquid oceans trapped between layers of ice for billions of years. It is this combination of external gravitational stress and internal nuclear fire that pressurizes these underground seas, forcing them to seek escape through cracks and weaknesses in the overlying icy crust, resulting in the spectacular, cold eruptions we observe. This immediately leads us to one of the most exciting prospects in all of modern science, the potential for life. The existence of cryovolcanoes is the most powerful indirect evidence we have for a global subsurface ocean. On Earth, we have found entire ecosystems thriving in the absolute darkness around hydrothermal vents on the ocean floor, deriving their energy not from the sun, but from the heat and chemicals spewing from the planet's interior. A world with a subsurface ocean heated by tides and radioactivity presents an almost identical scenario. The icy crust acts as a protective shield against radiation and asteroid impacts, while the cryovolcanoes themselves act as conduits, cycling nutrients and minerals from the rocky seafloor up toward the surface. Life in such an environment could be microbial, or it could be far more complex, perhaps even multicellular organisms that have evolved to thrive in perpetual darkness under immense pressure, in waters that are both life-giving and lethally cold. To witness the majesty of such an eruption is to see our own world's volcanism reflected in a frozen mirror. A CGI flyover would begin with a panoramic view of an impossibly smooth, cratered plain of pristine ice. Suddenly, our attention is drawn to a vast, dome-shaped mountain, its flanks stained with strange, reddish-brown deposits. As we zoom in, the ground around its base begins to fracture, and with a slow, powerful heave, a brilliant white plume of water ice, ammonia crystals, and organic compounds erupts into the black sky. Unlike the violent, explosive burst of an Earth volcano, this is a more fluid, geyser-like fountain, a continuous, towering jet that can persist for days or even years. The ejected material, no longer confined by the pressure from below, instantly freezes in the vacuum, creating a fine, glittering mist that settles back to the surface, slowly building up the volcano's caldera in delicate, layered rings of exotic snow. We are not merely speculating about such a world. We have a local example that proves the concept. In our own solar system, Saturn's moon Enceladus is a perfect, smaller-scale analog. The Cassini spacecraft famously photographed enormous plumes of water vapor and ice grains erupting from fissures near its south pole, providing definitive proof of a global subsurface ocean. Future missions are being designed to fly through these very plumes, analyzing their composition for the chemical building blocks of life. The cryovolcanic world in NGC 262, however, appears to be Enceladus on a planetary scale. The eruptions are more powerful, the potential ocean is vaster, and the energy sources are even more pronounced. Studying this distant, active world allows us to extrapolate what the future might hold for Enceladus and other icy moons, giving us a glimpse into a much more advanced and dynamic stage of cryovolcanic activity. It demonstrates that the processes we are only beginning to understand in our celestial backyard are not unique, but are likely a common and profoundly significant feature of frozen worlds throughout the cosmos. But just as we map the grand architecture of dark matter and the slow geological pulse of icy volcanoes, our investigation brings us to a challenge against one of physics' most sacred constants, the speed of light itself. Throughout the cosmos, this speed is regarded as the universe's ultimate speed limit, an unchanging 186,282 miles per second in the vacuum of space. Yet, within the vastness of NGC 262, astronomers are confronting a baffling series of observations collectively known as the light speed lag anomaly, where the light from specific cosmic events appears to be running late, or in some rare cases arriving suspiciously early, as if the rules of the road have suddenly changed. This isn't a simple case of miscalculated distance. It's a persistent, measured discrepancy that hints that the cosmic speed limit might not be quite as absolute as we once believed. To understand the sheer precision required to detect such a subtle effect, you have to appreciate the tools and methods used. Astronomers rely on what are known as standard candles, certain types of celestial events or objects whose intrinsic brightness is so well understood that we can calculate their true distance based on how dim they appear to us. The most important of these for this research are Type Ia supernova. These stellar explosions, occurring when a white dwarf star is pushed over its mass limit, always reach nearly the same peak brightness. By observing how bright or dim one appears, we can determine its distance with remarkable accuracy. We then measure the redshift of the galaxy it resides in, how much its light has been stretched to longer wavelengths by the expansion of the universe, which tells us how long that light has been traveling to reach us. In a universe with a constant speed of light, the distance calculated from the supernova's dimness and the distance calculated from its redshift should match perfectly. In several key instances within NGC 262, they do not. The light seems to have taken a slightly longer journey, arriving a fraction of a percent dimmer than the redshift data says it should be, implying a delay that has no conventional explanation. This seemingly minor discrepancy sends shockwaves through the foundations of modern physics, directly challenging the cosmological principle that underpins Einstein's theory of relativity. This principle states that the universe is homogeneous and isotropic. It looks roughly the same in all directions and from every point. The laws of physics, including the speed of light, are universal constants. If the light from these supernovae is genuinely lagging, it suggests that space itself in this region might have different properties. One radical explanation is that the vacuum of space is not completely empty. It is filled with a quantum energy field. Most theories assume this energy is uniform, but what if it fluctuates? In regions where this quantum foam is more energetic or dense, it could, in theory, create a kind of drag on light, slightly slowing its passage. It would be analogous to light moving through water or glass, where it travels slower than in a vacuum, but on a cosmological scale. The early arriving light is an even greater puzzle, potentially pointing to a phenomenon where the light takes a microscopic shortcut through the quantum foam of spacetime itself. The implications of a variable speed of light are so profound that they reach into the very heart of cosmology, forcing us to reconsider the universe's expansion rate, known as the Hubble constant. This number is crucial. It tells us how fast the cosmos is stretching and allows us to calculate its age and ultimate fate. Currently, there is a persistent and troubling tension between different methods of measuring the Hubble constant. They don't agree. If the speed of light has varied over time or across different regions of space, it would resolve this tension instantly. An inconstant c would mean that our measurements of cosmic distances, which all rely on the constancy of light speed, have a subtle built-in error. Our entire cosmic distance ladder, the tool we use to map the universe, would need to be recalibrated, potentially reshaping our understanding of everything from the size of the universe to the nature of the dark energy that accelerates its expansion. To make this abstract concept tangible, let's use a simple thought experiment. Imagine two identical cars leaving a city at the exact same moment, both destined for the same town 100 miles away. One travels on a perfectly smooth, newly paved highway. The other is forced to take a route that goes through a dusty, sandy patch for several miles. Even if both cars drive at the exact same speed on their respective roads, the car that had to drive through the sand will arrive slightly later. In this analogy, the cars are photons of light, the journey is across millions of light years, and the sandy patch is a region of space within NGC 262 where the properties of the vacuum itself might be creating a subtle cosmic resistance, causing the light to lag behind our most careful predictions. Unsurprisingly, these claims are met with intense skepticism and controversy within the scientific community. The majority of physicists hold firm to the constancy of the speed of light, as it is the bedrock upon which so much of our modern understanding is built. The leading counter-argument is that the anomaly is not evidence of a changing speed of light, but rather a sign of our own ignorance about the environment surrounding these supernovae. Perhaps the distant supernova's light is being subtly dimmed by previously undetected clouds of interstellar or intergalactic dust within NGC 262, making it appear further away than it truly is. Or maybe our models for the explosions themselves are imperfect, and these particular white dwarfs were slightly less massive or had a different composition, causing them to be intrinsically fainter than our standard candle assumption presumes. The debate is fierce, a tug-of-war between the revolutionary and the conventional, with each new observation from this distant galaxy adding another piece of evidence to an unresolved puzzle that strikes at the very core of our physical reality. As we ponder the fundamental constants of physics, our journey through the wonders of NGC 262 now reveals a structure of such profound elegance and familiarity that it seems to blur the line between the cosmic and the biological. Drifting through the void is a nebula unlike any other, a colossal filament of glowing gas and dust twisted into the unmistakable form of a double helix. This is the galactic DNA strand, a cosmic structure spanning several light years that mirrors the very blueprint of life here on Earth. To find a shape so intimately connected to our own existence mirrored on a scale of trillions of miles is an awe-inspiring and humbling experience, forcing us to confront a truly cosmic question. Is this breathtaking similarity a mere coincidence, or could it be a profound clue written in the stars about the origins of life itself? The sheer scale of this structure is almost beyond comprehension. If our entire solar system, from the Sun to the outer reaches of the Oort cloud, were placed next to this nebula, it would be a mere speck against one of its spiraling arms. The two strands of the helix, composed of ionized hydrogen and complex carbon-rich dust, spiral around a common axis, creating a vast, luminous corridor in space. The initial discovery was made by combining data from infrared and radio telescopes, which can peer through the obscuring dust to reveal the underlying architecture. When scientists processed the data and generated a three-dimensional model, the result was stunning. A perfect, large-scale double helix, looking for all the world like a molecule of DNA magnified to an astronomical scale. The immediate and instinctual question, of course, is how such a precise and familiar form could emerge from the chaotic forces of interstellar space. The leading natural explanation involves the powerful, invisible hand of magnetic fields. Imagine the central region of this nebula as a rotating disk of gas and dust, much like a young solar system in its earliest stages. This disk is permeated by incredibly strong magnetic fields. As the disk rotates, it drags these magnetic field lines along with it, twisting them into a tightly wound spiral. Charged particles within the plasma, the superheated, ionized gas, then become trapped along these twisted field lines, much like beads on a twisted wire. The particles stream along the helical paths, lighting them up and making the invisible magnetic structure visible. This creates the two glowing strands we observe. It's a dynamic sculpture carved not by chisel, but by the fundamental forces of magnetism and motion, a testament to how simple physical principles can generate astonishing complexity across the cosmos. Yet, the mystery deepens considerably when we analyze what this cosmic helix is made of. Spectroscopic analysis, which breaks down the light from the nebula into its constituent wavelengths, has revealed a chemical treasure trove. We are detecting the clear signatures of complex organic molecules, the very building blocks of life. There are polycyclic aromatic hydrocarbons, which are sprawling, carbon-based molecules often found in space, but also more exciting compounds like formaldehyde, hydrogen cyanide, and even simple amino acids like glycine. Finding these probiotic molecules in such a vast, organized structure is like discovering a fully stocked lumberyard and toolbox arranged perfectly to build a house. It doesn't mean the house has been built, but it shows that the most critical raw materials are not only present, but they are concentrated and arranged in a way that seems eerily purposeful. This has led some astrobiologists to wonder if the double helix shape is more than just a magnetic accident. Could it be a physical manifestation of the same organizational principles that govern life? Perhaps the conditions that lead to complexity, whether in a strand of DNA or in a swirling nebula, follow a similar set of patterns, a universal tendency for order to emerge from chaos in specific, efficient forms. To truly appreciate the majesty of this object, we must rely on stunning visualizations. Picture an animation that begins with a wide-field view of the spiral arm of NGC 262, filled with the soft glow of countless stars. We then zoom in towards a faint, wispy patch. As we get closer, the structure resolves, revealing two intertwined ribbons of brilliant pink and ethereal blue, glowing against the blackness of space. Our virtual camera then flies along the length of the helix, soaring past towering clouds of dust that obscure parts of the structure, giving it a textured, almost fibrous appearance. The final shot dives right into the heart of one of the glowing strands, where the visualization shifts to the molecular scale. We see the actual organic compounds, the carbon chains and water ices, coming together along the magnetic pathways, illustrating the direct link between the cosmic architecture and the chemistry happening within it. This remarkable nebula inevitably sparks a profound philosophical debate about the universe and our place within it. The double helix is a symbol of life on Earth, the very code that defines every living thing. To see that shape mirrored in the heavens feels significant, almost as if the universe is hinting that the principles of life are woven into its very fabric. This idea, known as the biological universe or cosmic pluralism, suggests that life is not a rare, random accident on a single planet, but a natural and common outcome of cosmic evolution. The galactic DNA strand could be seen as a giant billboard announcing that the universe is, in fact, bio-friendly, that the ingredients and even the patterns of life are ubiquitous. This doesn't mean the nebula itself is alive, but it powerfully suggests that the path from non-life to life may be a well-trodden one, with signposts like this one scattered throughout the galaxy. It stands as a breathtaking reminder that we are not separate from the cosmos. We are a conscious expression of its same underlying creative forces. But just as we contemplate the grand helical patterns of cosmic DNA, our investigation takes a sharp turn inward, plunging into the very foam and fabric of spacetime itself. We now arrive at our 25th phenomenon, a place where the smooth, continuous universe described by Einstein's general relativity appears to break down into a seething, turbulent frenzy. This is the quantum foam vortex, a region of space where our most powerful telescopes have detected effects that suggest the vacuum of space is not empty and smooth, but is a chaotic, frothing sea at the tiniest imaginable scales. To understand this, we have to shrink our perspective from the galactic to the subatomic, to a realm where the very concepts of here and now become meaningless. The idea of quantum foam was first proposed by the physicist John Wheeler in the 1950s. He theorized that if we could peer down to scales a trillion times smaller than an atom, the placid geometry of spacetime would dissolve into a state of violent, unpredictable fluctuations. At this level, governed by the bizarre rules of quantum mechanics, empty space is anything but empty. Virtual particles, pairs of matter and antimatter, constantly pop into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and returning it. Simultaneously, the fabric of spacetime itself is thought to be warping and twisting, forming a turbulent landscape of tiny, churning wormholes and constantly changing topologies. It's a bit like looking at the surface of a calm pond. From a distance, it seems perfectly smooth and glassy. But if you could get down to the molecular level, you would see a frantic, jostling dance of water molecules constantly moving and shifting. The quantum foam vortex is a place where this microscopic frenzy somehow manifests on a scale our instruments can indirectly detect. So how do we observe something that, by definition, exists at a scale far beyond our direct vision? The key lies in studying the light from the most violent objects in the universe as it passes through this region. The primary instruments are gamma-ray telescopes like the Fermi Gamma-Ray Space Telescope. Gamma rays are the most energetic form of light, with wavelengths so short they are comparable to the hypothesized scale of the quantum foam itself. As these high-energy photons travel across billions of light-years from distant blazars, supermassive black holes shooting out jets of radiation, they are essentially probing the fine-grained structure of spacetime along their path. According to one leading theory, the frothy nature of spacetime at the quantum level should act like a kind of cosmic fog for these specific photons. Just as light twinkles when it passes through the turbulent pockets of Earth's atmosphere, the highest energy gamma rays should experience a slight but measurable delay compared to their lower energy counterparts if their path takes them through a region of intense quantum foam. It is an effect of unimaginable subtlety, but by collecting vast amounts of data over years, a pattern has emerged from this specific vortex in NGC 262 that aligns with these theoretical predictions, as if the fabric of space has a detectable texture. To make this incredibly abstract concept tangible, let's use a vivid analogy. Imagine spacetime is the surface of the ocean on a perfectly calm, windless day. A sailboat can glide across it smoothly and predictably. This is the universe as described by classical physics. Now imagine a violent storm hits. The surface erupts into a chaos of waves, whitecaps, and churning bubbles. This stormy sea is the quantum foam. Now picture two different kinds of boats trying to cross this turbulent water. A large, slow barge representing low-energy light would plow through the chaos relatively unaffected, its course barely altered. But a small, incredibly fast speedboat representing a high-energy gamma ray would be jostled, bumped, and slightly slowed down as it slams into the countless tiny bubbles and waves. This is the essence of the light-speed lag we detect. The highest energy photons are the ones most sensitive to the underlying frothiness of spacetime, and their slight delay is our first indirect glimpse of this hidden, turbulent reality. The existence of this vortex provides critical, real-world support for the long-sought theory of quantum gravity. For decades, physics has been divided into two brilliantly successful but incompatible kingdoms. General relativity masterfully describes the universe on the largest scales: the force of gravity, the bending of space-time, and the dynamics of galaxies and black holes. Quantum mechanics, with equal mastery, describes the universe on the smallest scales: the behavior of atoms and subatomic particles. The problem is, they don't play well together. The equations of general relativity break down completely in the extreme conditions where quantum effects dominate, such as at the center of a black hole or at the moment of the Big Bang. A theory of quantum gravity aims to unify these two domains, and the quantum foam is a central prediction of several leading candidates, such as string theory and loop quantum gravity. The observations from this vortex are like finding a fossil that shows features of both mammals and reptiles. It doesn't give us the full theory, but it provides a crucial piece of evidence that we are on the right track, confirming that spacetime itself has a quantum granular structure. To visualize the unvisualizable, we turn to sophisticated computer simulations. Picture an animation that begins with a view of empty black space. As we zoom in at an exponentially accelerating rate, passing through atoms and nuclei, we finally arrive at the Planck scale, the fundamental limit of smallness. Here, the screen erupts into a dynamic, churning display. Spacetime is no longer a flat grid but a bubbling, effervescent cauldron. Tiny wormholes, like microscopic tunnels, constantly form and collapse. Fluctuations in energy create transient, shimmering patterns. The geometry of this realm is not fixed. It is a probabilistic foam where the very notions of distance and duration lose their classical meaning. This simulation, while a vast simplification, gives us a visual metaphor for the incredible violence and complexity that underlies every single point in our seemingly calm and ordered universe. The quantum foam vortex in NGC 262 is our first macroscopic window into this hidden, foundational layer of reality, a place where the universe itself is being constantly rewritten and reshaped on a timescale too fast for us to comprehend. Yet for all the apparent chaos revealed by the quantum foam, the universe may possess a hidden order of a different kind altogether, a symmetry so perfect it creates an entire shadow reality existing alongside our own. This brings us to our 26th phenomenon, the mirror matter clouds. Picture this: drifting through the star fields of NGC 262 are immense, invisible structures. They exert a clear and measurable gravitational pull on the stars and gas around them, yet they remain completely transparent to every form of light we can throw at them. Radio waves, infrared, X-rays, all pass right through as if nothing is there. These are not clouds of dark matter. The gravitational signature is different, more structured. The leading explanation is that we are detecting colossal accumulations of mirror matter, a hypothetical substance that could form a hidden, parallel sector of the universe, one that intersects with our own only through the faintest of whispers, the force of gravity. The theory behind mirror matter is rooted in a quest for perfect symmetry in the laws of physics. Physicists have long noted a certain lopsidedness in our universe, particularly in the behavior of subatomic particles during certain types of radioactive decay, a phenomenon known as parity violation. It's as if the universe has a built-in preference for left-handedness. To restore this fundamental symmetry, the idea of mirror matter was proposed. It suggests that for every type of particle we know, electrons, protons, quarks, there exists a mirror twin. These mirror particles would be identical in mass to their normal counterparts, but they would interact with each other through their own set of mirror forces: mirror photons, mirror strong nuclear force, and mirror weak nuclear force. The crucial point is that these mirror forces do not interact with our normal forces. A mirror photon would be invisible to our eyes and our telescopes. The only bridge between our world and the mirror world is gravity, a force that both sectors share because it is a consequence of the geometry of spacetime itself. This leads to a breathtaking possibility. An entire invisible universe could be interwoven with our own. Mirror matter could form mirror stars powered by mirror nuclear fusion, giving off mirror light that we could never see. It could coalesce into mirror planets and perhaps even give rise to mirror life. These mirror matter clouds in NGC 262 could be the interstellar gas and dust of that parallel cosmos, their presence revealed only because their collective mass gently tugs on the visible matter of our own universe, warping its motion and bending the path of light in subtle but detectable ways. The evidence for this doesn't just come from gravitational anomalies. Precise measurements of the cosmic microwave background, the afterglow of the Big Bang, show patterns that some cosmologists argue could be explained by the gravitational influence of a mirror sector in the early universe. Furthermore, if these two sectors were created in the Big Bang, they would have been in thermal contact for a brief moment, and the specific ratios of light elements we see in the cosmos could also be a fingerprint of this mirror world's existence. Visualizing this concept requires a clever blend of the seen and the unseen. Imagine a stunning, multi-wavelength composite image of a vibrant nebula in NGC 262, its colors shifting from deep red to brilliant blue. Then we overlay the gravitational map of the same region based on painstaking measurements of stellar motions. A ghostly, translucent structure in shades of silver and gray materializes, superimposed over the brilliant nebula. This ethereal cloud has a defined shape, perhaps a swirling vortex or a series of dense filaments, but it doesn't obscure the normal matter behind it. The two coexist in the same space, one blazing with light, the other a silent, massive phantom. The visual makes it immediately clear that we are looking at two separate realities occupying the same volume, one that shouts its presence and one that can only be felt by its weight. The implications of confirming mirror matter would be nothing short of revolutionary. First, it would solve one of the most enduring mysteries in science, the nature of dark matter. These mirror particles are excellent candidates for the invisible mass that binds galaxies together, but it would do more than that. It would utterly transform our view of reality. We would have to accept that everything we see and touch and are made of is only half of the cosmic story. The universe would be twice as rich and complex as we ever imagined, with every galaxy, every star, and every person potentially having a silent, invisible double in a parallel realm that has evolved separately for nearly 14 billion years. The mirror matter clouds of NGC 262 are thus more than just another anomaly. They are a potential gateway to a hidden cosmos, a clue that the universe's greatest secret may not be tucked away in distant dimensions, but is right here beside us, woven into the very fabric of space, forever just beyond the reach of our senses. Of course, the life of a star is a story told over billions of years, a slow, majestic dance of birth, maturity, and eventual death written in the language of nuclear fusion and gravity. But in NGC 262, it seems some stars are in an incredible hurry, living their entire lives in a cosmic blink. We now encounter stars undergoing what can only be called a stellar metamorphosis, where a sun can transform from a cool, red giant into a hot, blue beacon in a matter of mere centuries, a process that should naturally take millions of years. It's as if these stars have discovered a secret shortcut through their own life cycles, changing their fundamental nature with a speed that defies every established model of stellar evolution. To understand just how strange this is, we need a quick primer on the Hertzsprung-Russell diagram, the fundamental map of stellar lives. This chart plots a star's temperature against its luminosity, and over its lifetime, a star traces a predictable path across this map. Our own Sun, for instance, is a stable main sequence star, destined to spend billions of years in a specific region of the diagram before slowly swelling into a red giant. The rapidly changing stars in NGC 262, however, are drawing chaotic, zigzagging lines across this map. long-term observations show a star identified as a mature orange-class K giant suddenly and rapidly heating up, its color shifting toward blue and its luminosity skyrocketing, effectively jumping from one corner of the HR diagram to another in an astronomical instant. This isn't a gentle aging process, it's a stellar identity crisis playing out on a timescale we can almost watch in real time. The most logical engine for such a dramatic transformation is a stellar merger or a period of extreme, gluttonous consumption. Imagine a solitary red giant, a vast, puffed-up star burning through the last of its fuel. Now imagine it has a dense, close companion, a white dwarf or a main sequence star. If their dance becomes unstable, the larger star can begin to violently strip material from its partner, or the two can collide and merge into a single new object. This sudden infusion of fresh hydrogen fuel, or the immense energy released by the collision itself, can violently reignite nuclear fusion in the star's core and envelope. The star, in response to this new internal energy source, rapidly contracts and heats up, shedding its red giant appearance to become a much hotter, bluer, and more luminous star. It's a cosmic facelift of the most extreme kind, powered by the catastrophic digestion of a stellar neighbor. This bizarre behavior forces astronomers to consider the existence of objects that were, until recently, purely theoretical. One of the most captivating possibilities is that we are witnessing the formation or the stable existence of a Thorne-Zitkow object, proposed by physicists Kip Thorne and Anna Zitkow. This is a hypothetical hybrid star, a Russian nesting doll of stellar bodies. It consists of a red giant or supergiant star with a neutron star at its very core, the remnant of a companion that spiraled in and was swallowed whole. In this configuration, the neutron star doesn't immediately cause an explosion. Instead, it sits at the heart of the giant, acting as an immensely powerful and unnatural engine. The nuclear processes around a neutron core are radically different, potentially producing unique elements and driving violent convection that could cause the enormous outer star to flicker and change its spectral class erratically. The detection of unusual abundances of elements like rubidium, lithium, and molybdenum in the atmospheres of some of these rapidly changing stars is considered a potential fingerprint of a Thorne-Zitkow object, a signature of the exotic physics occurring deep within a cannibalistic sun. The implications of this rapid metamorphosis ripple outward, challenging the very foundations of astrophysics. Our entire understanding of stellar evolution is built on the assumption of stable, long-term nuclear burning. Stars are classified and their futures predicted based on their mass and composition, with their journeys mapped on the HR diagram as smooth, predictable tracks. These shape-shifting stars of NGC 262 render those textbooks incomplete. They demonstrate that stellar lives can be punctuated by sudden, catastrophic events that reset their evolutionary clocks, turning a predictable timeline into a chaotic and dynamic story. This means that when we look at a star in any galaxy, we can no longer be entirely certain of its age or its fate. It might be an ancient star that has recently been rejuvenated, or a young star prematurely aged by a violent encounter. Visualizing this requires a dynamic, animated HR diagram. Picture the classic plot with its main sequence band and regions for giants and supergiants. A single data point representing one of these peculiar stars is highlighted. Instead of sitting still, this point begins to move. It darts upward and to the left, signifying a huge increase in both temperature and luminosity. It might pause, then slide back toward the right, cooling and dimming slightly before making another sudden jump. This animated path, a frantic scribble across the diagram, makes the star's instability viscerally clear. It's not following the rules, it's charting its own chaotic course, a celestial rebel whose life story is being written not in slow, geological time, but in the frantic pace of cosmic violence. The existence of these stellar chameleons forces us to see the galaxy not as a static collection of lights, but as a dynamic and sometimes violent ecosystem where stars can be born again, their destinies rewritten in the fire of collision and the strange physics of hidden, exotic hearts. But if you thought the strange phenomena of NGC 262 were limited to what we can see with light or feel with gravity, prepare to enter a realm of invisible bullets, subatomic particles screaming across the universe with energies so immense they defy belief. Our 28th discovery is a cosmic ray hotspot, a specific region of this galaxy that acts as a cosmic cannon, firing atomic nuclei and other particles at velocities so close to the speed of light that they carry more energy than a professional baseball pitch, but compressed into a single subatomic projectile. These are ultra-high-energy cosmic rays, and the sheer power concentrated in this one area of NGC 262 is far beyond what any known celestial engine should be able to produce, pointing to a source of unimaginable violence. To truly grasp the scale of this energy, let's put it in human terms. The most powerful particle accelerator on Earth, the Large Hadron Collider, can smash protons together with a combined energy of about 13 trillion electron volts. The cosmic rays streaming from this hotspot have been measured with energies exceeding 100 quintillion electron volts. That is a number with 20 zeros, millions of times more powerful than anything we can create. A single one of these particles, smaller than an atom, carries the kinetic energy of a rock falling from a tall building, all packed into a tiny bullet traveling at almost the speed of light. When such a particle strikes the upper atmosphere, it doesn't just quietly dissipate. It initiates a spectacular cascade, an avalanche of secondary particles that can spread over dozens of square miles, a phenomenon known as an extensive air shower. It is these grand secondary effects that allow us to detect these cosmic bullets at all. So what cosmic monsters could possibly be responsible for such incredible accelerators? The usual suspects in our own galaxy, like supernova remnants, simply don't have the power to reach these energies. In NGC 262, our gaze turns to far more extreme candidates. The prime suspect is an active galactic nucleus, the incredibly energetic core of the galaxy powered by its central supermassive black hole. As vast quantities of matter spiral inward, they can be funneled and focused by powerful magnetic fields into relativistic jets, beams of plasma shooting out from the poles at nearly light speed. Shockwaves within these jets could act as a natural particle accelerator of staggering size and power, capable of pumping protons and atomic nuclei up to the extreme energies we observe. Another terrifying possibility is a recent gamma-ray burst, the most luminous electromagnetic event known in the universe, born from the collapse of a hypermassive star or the merger of two neutron stars. The afterglow of such a cataclysm could provide the perfect environment for particle acceleration, leaving behind a temporary but incredibly powerful beacon of cosmic rays. Then there is a more exotic and perhaps more fundamental explanation: annihilating dark matter. Some theories suggest that dark matter particles could be their own antiparticles. If this is true, then where dark matter is exceptionally dense, these particles could collide and annihilate each other in a burst of pure energy, producing a shower of standard model particles, including the high-energy protons and nuclei we detect as cosmic rays. The hotspot in NGC 262 could coincide with a dense clump of dark matter, a place where this invisible substance is actively destroying itself and, in the process, revealing its presence through a fountain of ultra-high-energy debris. This would mean we are not just looking at a powerful engine, but at the direct decay signature of the universe's most mysterious component. Detecting these elusive particles is one of the greatest technical challenges in modern astrophysics. Because cosmic rays are charged, their paths are bent and scrambled by the magnetic fields that fill interstellar and intergalactic space, making it impossible to simply trace a straight line back to their source. We have to become cosmic detectives using enormous indirect observatories. The two primary methods are giant ground arrays and fluorescence detectors. A ground array, like the Pierre Auger Observatory in Argentina, consists of thousands of water tanks spread over 3,000 square kilometers, an area larger than some small countries. When the particle shower from a single cosmic ray rains down, it produces a faint flash of light in these tanks, allowing scientists to reconstruct the energy and arrival direction of the primary particle. Fluorescence detectors, on the other hand, watch the night sky for the faint ultraviolet glow that the air shower itself produces as it develops high in the atmosphere. By combining data from both techniques, we can build a statistical map, and it is this map that reveals a clear, significant excess of these ultra-high-energy events, pointing back to the NGC 262 hotspot. To understand the journey of one of these particles, an animation is invaluable. Picture a single proton represented as a shimmering point of light being ejected from the turbulent jet of the galaxy's central black hole. It begins its multi-million-year journey across the intergalactic void. As it travels, we see it pass through a labyrinth of swirling magnetic fields, shown as faint blue lines. With each gentle curve, the proton's path is deflected until its original direction is completely lost. Finally, it reaches the edge of Earth's atmosphere. The moment it collides with an air molecule, the screen erupts in a spectacular, branching cascade of energy. Trillions of secondary particles, electrons, muons, photons, fan out in a widening cone, propagating down toward the surface, where an array of detectors lights up in sequence, capturing the aftermath of this tiny, yet immensely powerful interstellar traveler. This invisible rain of high-energy particles is not just a scientific curiosity. It poses a very real and practical danger to both technology and human explorers. For satellites in orbit, a direct hit from a cosmic ray can cause a single event upset, flipping a single bit in a computer's memory from a 0 to a 1 or a 1 to a 0. This can lead to unexplained glitches, corrupted data, or even the complete failure of a critical system. For future astronauts on long-duration missions to Mars or beyond, the threat is even more severe. Outside the protective bubble of Earth's magnetic field and atmosphere, they would be constantly bombarded by this radiation. A single high-energy cosmic ray particle tearing through a spacecraft wall and through an astronaut's body could damage DNA and kill cells, significantly increasing the lifetime risk of cancer and posing a major hurdle for human expansion into the solar system. Studying hotspots like the one in NGC 262 is therefore essential for space weather forecasting and for designing the radiation shielding that will one day protect interplanetary travelers. This phenomenon connects the most violent events in a distant galaxy directly to the practical challenges of our own species' future in space, a reminder that the cosmos is not only a place of wonder, but also an environment we must learn to navigate with caution. Having charted the courses of cosmic rays and witnessed the frantic evolution of stars, we now turn our senses to a more fundamental vibration, one that stretches and compresses the very fabric of reality. Throughout our journey, we've encountered gravitational waves from the singing black hole, but those were rhythmic pulses, a cosmic melody. Now we find something subtly different and profoundly persistent, a binary system emitting continuous gravity wave ripples. Imagine not a single drumbeat, but the unwavering low hum of a massive engine. This is the sound of space-time itself groaning under the strain of two immense objects locked in an eternal, spiraling dance, broadcasting their slow-motion fate across the universe in a whisper we are only just learning to hear. The way we detect these signals is a triumph of human ingenuity and patience. Instruments like LIGO and Virgo are exquisitely tuned to catch the sudden, cataclysmic chirps of black hole or neutron star mergers, events that are violent and brief. But to hear the continuous hum from a system like this one requires a different approach altogether. It's the difference between trying to hear a single clap in a silent room and trying to pick out the steady pitch of a distant power plant from a constant city roar. Astronomers must sift through years of data, meticulously filtering out the noise of seismic activity, passing trucks, and even quantum fluctuations at the atomic scale. By combining observations from multiple detectors across the globe and employing sophisticated data analysis techniques that can lock onto a single, unchanging frequency, they can finally isolate this faint, unwavering signal. It is the astrophysical equivalent of finding a needle in a cosmic haystack, not by looking for something sharp, but by listening for a specific, sustained note. This constant hum is a treasure trove of information, a direct broadcast of the system's most intimate dynamics. The primary message encoded in these ripples is one of inevitable orbital decay. According to Einstein's theory, as these two massive bodies, likely a pair of neutron stars or white dwarfs, orbit each other, they lose energy by radiating gravitational waves. This loss of energy causes their orbits to slowly, inexorably shrink. The continuous gravitational waves allow us to measure this in-spiral with phenomenal precision. By tracking the gradual increase in the frequency of the waves over months and years, we can calculate exactly how much the stars are drifting closer together and predict, with astonishing accuracy, when they will finally merge, an event that might be hundreds of thousands or even millions of years in the future. Furthermore, if the orbits are not perfectly circular, we can detect a wobble known as precession, where the orientation of the orbital plane itself slowly rotates over time. This precession leaves a specific fingerprint on the gravitational wave signal, revealing the intricate details of the star's mutual gravitational pull and their internal structure. To truly appreciate the beauty of this phenomenon, we can visualize it with a stunning simulation. Picture a calm, grid-like representation of spacetime, a flat, undisturbed sheet. Now place two dense, glowing orbs onto this sheet, orbiting each other rapidly. As they move, they don't just roll across the surface, they generate persistent, expanding ripples like two children running in circles on a trampoline, creating a continuous, undulating deformation in the fabric beneath them. These ripples propagate outward at the speed of light, not as a single burst but as an endless, coherent wave train. The simulation would show these waves stretching and squeezing space itself in a perpetual, rhythmic pattern, a testament to the unending dynamism of even the most seemingly stable systems. The detection of these continuous ripples marks a monumental leap for gravity wave astronomy itself. For decades, this field was a theoretical promise. Then we learned to hear the universe's loudest crashes. Now, with the ability to detect these persistent signals, we are learning to listen to its background hum, its everyday conversations. This opens up an entirely new spectrum of observation. We can now monitor binary systems in real time, watching their slow cosmic waltz play out over human timescales. This new data provides a direct test for general relativity in a regime of strong gravity over extended periods, allowing us to probe for any minute deviations that might hint at new physics. It also turns these binary systems into standard sirens of unparalleled precision. By knowing their exact orbital parameters from the gravitational waves, we can independently calculate their distance, providing a new and incredibly accurate ruler for measuring the scale of the universe and refining our value for the Hubble constant. This gentle, unending whisper from a distant star system is therefore more than just a curiosity. It is a precision tool, a cosmic metronome that is helping us fine-tune our understanding of the cosmos, from the behavior of matter under extreme pressure to the very expansion rate of space itself. And so we arrive at the final and perhaps most profound mystery in our journey, a phenomenon that teeters on the precipice between natural wonder and the long-dreamed of signature of intelligence itself. Far from the galactic core, orbiting a seemingly ordinary star, we find evidence of something that has consumed more energy and more speculation than almost any other concept in science fiction: a Dyson swarm. The clues are subtle, written not in radio broadcasts or laser beams, but in the ancient, patient language of starlight. The star in question exhibits a pattern of dimming so bizarrely irregular that it defies all conventional explanation for planetary transits. It doesn't fade in the clean, symmetrical, and predictable way a planet would, blocking its light for a few hours every year. Instead, its light dips erratically by wildly varying amounts and for unpredictable durations. Sometimes it dims by just a fraction of a percent. Other times, its brilliance is slashed by more than 20%, as if a colossal, uneven shroud is constantly shifting and reforming around it. This baffling light curve was first spotted by the Kepler Space Telescope, an instrument designed to find new worlds by watching for the gentle, repeating winks of planets. But this star was not winking, it was blinking in a chaotic, almost nervous pattern. The immediate and most cautious explanation points to a massive, chaotic cloud of dust and debris, perhaps the aftermath of a colossal planetary collision, a cosmic traffic accident of epic proportions. Such an event could fill a star system with trillions of irregular, tumbling fragments of rock and ice, which would indeed block light in an uneven, messy way. Yet, when astronomers turned other instruments toward this star, they found a second critical piece of the puzzle: an excess of infrared radiation. A young, dusty debris disk glows brightly in infrared, the heat signature of warm dust. But this star is mature, and the infrared signal, while present, is not as strong as a natural debris disk should produce. It's as if the dust is there, but it is unusually cold or perhaps being deliberately managed. This combination, the bizarre, aperiodic dimming coupled with a puzzling infrared signature, is what makes the case for a Dyson swarm so compelling to some scientists. The concept proposed by physicist Freeman Dyson is one of staggering scale. A single, solid shell around a star is considered physically impossible, but a swarm is different. Imagine not one structure, but countless billions of them, vast solar collector satellites, habitats, and industrial platforms, each on its own independent orbit around the star, forming a loose, thick cloud. This collective would capture a significant portion of the star's light for energy, converting it to useful work and then re-radiating the waste heat as lower-energy infrared light. From our distant vantage point, we would see exactly what we are seeing: the star's visible light flickering unpredictably as these vast orbiting structures pass in front of it, while the system glows with the telltale warmth of their technological activity. The irregularity of the dimming is the key. A natural cloud would tend to smooth out over time, while a living, evolving swarm of constructs would be in constant flux, with new platforms being built and old ones decommissioned, creating an ever-changing silhouette against the star. This discovery forces us to directly confront the chilling silence of the Fermi paradox. If the universe is so vast and so old, where is everybody? The potential existence of a Dyson swarm provides a haunting possible answer. A civilization capable of such engineering would have reached a level of development, a Kardashev Type 2 status, that is literally unimaginable to us. Their energy consumption would dwarf our entire planetary output by a factor of trillions. Such a culture might have absolutely no interest in or need for broadcasting its presence on primitive radio waves that we can detect. Their communication might use neutrino streams or quantum-entangled particles, technologies that are completely invisible to our current search methods. They would be, for all intents and purposes, silent ghosts, their presence discernible only by the shadow they cast upon their sun, a signature of technology so advanced that to us it appears almost as a force of nature. They wouldn't be hiding from us, they would simply be operating on a level so far beyond our own that we are like ants on a jungle floor, unaware of the sprawling city just beyond the trees. To visualize this awe-inspiring concept, we turn to the artist's impression, a rendering that attempts to capture the sheer, mind-boggling grandeur of such an achievement. The view begins on a hypothetical world within the system, its sky dominated by a star partially obscured by a sprawling, geometric tapestry. Countless hexagonal and rectangular panels, each one likely larger than our entire planet, form a complex, incomplete web across the face of the Sun. In the black space between them, we might glimpse the moving points of light that are orbital habitats, each one a world in its own right. The overall impression is not of a single structure, but of a dynamic, living matrix, a technological ecosystem that has wholly enveloped its star, having moved beyond the need for planets entirely. The civilization that built this would have effectively conquered scarcity, possessing energy and resources on a scale that would allow them to shape their own cosmic destiny in ways we can only dimly perceive. The search for such technosignatures is now a serious and growing branch of astronomy, moving beyond listening for signals to actively looking for the physical evidence of astroengineering. This star in NGC 262 is not alone. Several other candidates with similarly strange light curves have been identified in our own galaxy, each one a puzzle box waiting to be opened. The next generation of telescopes, like the James Webb Space Telescope and its successors, will be crucial. They will be able to analyze the spectra of the starlight filtering through this mysterious swarm with incredible precision, looking for the chemical fingerprints of industrial processes, unusual ratios of elements, or the presence of artificial compounds that would never occur in a natural debris disk. Finding such a fingerprint would be the most profound discovery in human history, fundamentally altering our understanding of our place in the cosmos. It would tell us that we are not the first nor the greatest, and that the story of intelligence in the universe is far older and more magnificent than we ever dared to dream. So as our tour of these 30 marvels concludes, we are left not with a final answer, but with the ultimate question hanging there in the silent, dark space between the stars. Are we alone as a thinking species, or are we merely the newest members in an ancient, sprawling, and unseen galactic community? The evidence from NGC 262 suggests the cosmos is stranger and potentially far more crowded than we ever imagined. And so our journey through the celestial cabinet of curiosities that is the NGC 262 galaxy comes to a close. We have wandered past the silent, ghostly flicker of the phantom-nebula, felt the rhythmic heartbeat of the singing black hole, and marveled at the prismatic beauty of the crystal planets. We have witnessed time itself bend in the Chronos anomaly, puzzled over the instant connection of quantum-entangled binary stars, and seen the void itself take on a strange semblance of life within the living dust clouds. From the backward spinning heart of the galaxy to the perfect mathematical harmony of resonant worlds, each phenomenon has been a profound lesson in cosmic humility, showing us that for every law we write, the universe seems to have an exception waiting in the wings. These are not just fleeting oddities, they are the very frontiers of human understanding, the places where our current models of physics and cosmology stretch, strain, and sometimes crack under the weight of new, astonishing evidence. This grand tour does more than just catalogue wonders, it fundamentally reshapes our perspective on reality. It teaches us that the cosmos is not a static, predictable machine, but a dynamic, evolving, and deeply interconnected system, brimming with forces and phenomena we are only beginning to comprehend. The silence of the radio silence zone and the structured complexity of the galactic DNA strand suggest that life and intelligence could manifest in ways we have not yet even considered, challenging our very definitions of what it means to be alive and conscious in the universe. The light-eating void and the dark matter fountain reveal that the majority of the cosmos is made of stuff we cannot see, forcing us to probe the darkness with new tools and new ideas. Each mystery in NGC 262 is a pointed question, an invitation to look deeper, to question more fiercely, and to remain forever curious in the face of the great, beautiful unknown. Ultimately, the greatest legacy of this exploration may not be the answers we have found, but the vast and thrilling expanse of questions that remain wide open. The existence of these phenomena proves that our current understanding is not the final word, but merely the opening chapter in a story that is still being written across billions of light years. It is a powerful reminder that discovery is not a destination, but a continuous journey. Every time we build a more powerful telescope, launch a new observatory, or develop a fresh theoretical model, we open another window onto this incredible cosmic menagerie, ready to be surprised all over again. The universe is not yet done revealing its secrets, and that is the most exciting prospect of all. We would love to continue this conversation with you. Looking back over these 30 marvels, which one captured your imagination the most? Was it the silent, sentient-seeming intelligence of the Proteus Nebula, or the physics-defying straight-line paths of the gravity-defying comets? Perhaps it was the chilling possibility of the Dyson Swarm, a signature of intelligence on a scale we can scarcely fathom. Share your favorite in the comments below and tell us why it resonates with you. Your perspective adds another valuable voice to this collective quest for understanding. If this voyage into the strange has sparked your curiosity, be sure to subscribe and hit the notification bell so you can join us for our next cosmic adventure. There are countless more galaxies, each with their own unique mysteries, waiting just beyond the edge of our current maps. Keep your eyes on the skies and your mind open to wonder, because the next great discovery, the next paradigm-shattering revelation, is always just one observation